as exemplified by Alex's discussion just
Yeah, I made like 4 of them so far.
I'd like to apologise in advance. Like the previous presentations, my slides are not going to be legible from anyone sitting behind the first row. So those of you who have smartphones or laptops, please go there. I'll give you a couple of minutes. You'll find this entire presentation online at that link, and then you can look at your screens. Hopefully that's useful. I was given a very long title in the schedule, and I decided to retitle it. Going back to a 1965 movie that's a particular favourite of mine, which is entitled Those Magnificent Men and Their Flying Machines. And I think what we can do with that, because we're not in 65 anymore, we're now in 2018, is of course we have to address gender equality, so men have to become men and women. But I'd like to change that to those magnificent men and women and their dispensing machines, and show you what I think is impressive about what's already been done with acoustic dispensing in crystallography, which is my field, and how I think crystallography can play a role in drug discovery in the context of acoustic dispensing, where its powers are and where its weaknesses are. This is also going back to my family. My father infected me with this line from Colonel Manfred from Holstein. It's a tip of the hat to the Germans in the audience, because the quote is, "There is nothing a German officer cannot do." And I have changed it to, "There's nothing a physicist cannot do." I'm a physicist. And I'd like to propose, actually, there's very little that acoustic dispensing cannot do in some way better or worse than other things. So, the overall structure will be something like this. I hate it when people do this for their presentations, but the intention is to give you time to download this. So I will kind of follow on or summarise current approaches where I think the powers and the weaknesses are with the vision of crystallography. What I see as future trends, this is blue sky. I give you fair warning. I was called by a friend in Oxford in 2000 and something, and he said, "I've got a phone call recently from California, and they talked to me about DNA and sticking it onto plastic, and should I get involved in this?" And I said, "No, this sounds daft." And about 10 years later, he called me up and said, "That was Affirmatrix. Oops, you owe me $10 million. So I have been very wrong in the past, very wrong. I will mention also stuff we're trying to do directly with Daisy that's somehow peripheral but yet integrated with this entire workshop, a project we call Extreme. So, my first experience of acoustic dispensing came at the NSLS 2 user meeting in 2010. I was invited up to New York. I met Alex de Suarez and the rest of them, and amongst other things, they showed me the use of these little droplet machines to do things in crystallography. And this was really cool. I didn't know how far it would go at the time. And I'd like to take an exception to something that was said in the morning, that I don't think is necessarily the way forward for acoustic dispensing in crystallography. What they had done, as was expressed, is they moved microcrystals that are produced in slurries of high density onto a raster, a loop here, okay? And then use this to perform serial crystallography. Each microcrystal is diffracted, the data sets are merged, you end up with a structure. Now, this, I think, is a misuse of the technology, quite simply because I know myself, I've done this, but if you simply take this same loop and dip it through slurry mixture, you will pick up the same number of microcrystals. And it's been done on the NBL beamlines. You can do the same studies, you can do serial crystallography on these things. So here, ADC is not really doing anything novel, and actually nothing that can't be done by a PhD student with a pot and a hammer. What it has done, however, is it was part of the way in which crystallography became more physics-based again. So back in the day, Tom Gundell, Louise Johnson, crystallography was a physics science. Yes. It became a biological science to the point where a physicist like me walked in and said, "Yeah, but you don't know what you're doing with these X-rays. You're asking biological questions without understanding physics." So that was great for me. I could build a career. However, with the advent of people like Henry Chapman, And those of you who are of a betting nature, Henry is nailed on certainty for a Nobel Prize sometime in the next 3 or 4 years. What he did as a physicist, coming into the field of protein crystallography, is start to look at things again. And he adopted approaches like this, of using liquid jets to move nanocrystals around in the same way, particularly to do studies on FELs, such as the one being built or being operated in DAISY currently. One of his misconceptions, also current to this, and that was a lovely conversation I had with Henry in 2010, was this idea that microcrystals are easier to grow. It's actually an Alexi's paper, and I tell you here and now, that is a lie. Microcrystals are still large assemblies of hundreds of proteins. Kinetically, they are no more challenging to grow than an assembly that is thousands. We're talking about moving from single molecules to an ordered array, and whether that lattice is 10, 20, or 100, the kinetics are the same. Once you have conditions that grow microcrystals, you can grow macrocrystals. And this is exemplified by a follow-up paper to Henry's work on photosystem 2. So he shot his photosystem 2 crystals through an FEL, collected 100,000 images, reconstituted a 3.9 angstrom map of PS2. A Japanese group saw this paper, took his recipe to grow microcrystals, used that as a purification step, grew one single crystal out of that, and published a 1.8 angstrom structure. Microcrystals better? No. But they are useful to purify things. So here I think AD falls down. And his second point was that beam flux, moving to stereocrystallography, is inevitable. I think this is also fundamentally incorrect. This whole process of damage before destruction, data collection before destruction, is fundamentally flawed. Okay? This idea that you can move things across in nano environments, expose them to massive doses of X-rays, and you're not going to see knock-on effects as you collect, is physically not possible. I should also mention, although that was my first meeting with acoustic dispensing, when I went through the literature, I actually found a paper going back to 1927. So it's been around a time. Here is another reason I think stereocrystallography is not the route to go. This is from Alexi's paper, and this is the electron density from a serial system. This is what you get when you put insulin as a single crystal on a beamline. You get far better maps. The process of averaging distinct samples creates inhomogeneities in data. This is particularly important when you're looking to see the pose of fragments within a crystal, because you can imagine that here, I know the structure. I know where to put things, because I've done this before. But if I'm looking for a new chemical entity bound to this, distorted electron density will lead me down the wrong routes. It will take me to the wrong molecules. Okay? Because this shape is all I have to detect what that molecule is. And this is where I'm going to borrow from Dorothy Crowfoot-Hodgkin, who should have got a Nobel Prize with Watson and Crick, and say, well, back in 1935, the process of diffraction was stunning, but please note, it took almost 35 years to move from the observation, experimental collection, to actually moving to interpretation. And that's very important here when you start talking about any science. Collecting data is not the same as being able to use that data. And very often, you do need 35 years to fully understand all the processes involved. Okay? And when you're talking about $2.5 million per day for a blockbuster, 30 years, you can imagine, is a lot of time to not understand what you're doing. Okay? So I think, in this case, acoustic dispensing doesn't really have the power of other methods. On the lab site website, there's also a link to this kind of technology. And here, there's been some very impressive work done on miniaturizing protein crystallization. But again, we run into a philosophical wall here, which is, as you minimize things, you're doing more of the same experiments for less volume, which is smart in a way. But then I'm going to quote Einstein. The definition of insanity is doing the same thing all the time and expecting a different result. This is a way to do the same thing much, much more. You're not understanding what you're doing, you're screening more. And in perfect situations, that can lead to entire campaigns based on 12 microliters of sample. Beautiful, but I challenge anyone with Ingenentech to produce pure samples on a 12 microliter scale, reproducibly. I do this for a living. You cannot do it. You need to be making bigger samples to get good samples. That's just how purification and concentration work. These additional approaches with the droplet transfer have also been mimicked with inkjet approaches, and there are plenty of examples of sitting drops that have been set up to grow crystals, also in the presence of oil in microfluidics, that start to approach these 50 nanometer scales. So this is not a quantum leap either. It is very impressive for different reasons. And here I think is where we start to talk about what the dispensing can do. So the first one is very obvious. This is a paper I give to my students all the time to read. And it's this concept of using robotics to dispense nucleation from crystallization into then sparse matrix screening. And this is something that becomes exponentially more complex the more you want to do. So a standard crystallization screening, Bernard Rupp would tell you, is 400 conditions. That's what we need to cover crystallization space, roughly. Those 400 conditions will give you empty drops, drops with something in, and if you're very lucky, crystals, but very often nothing. Okay? What Alan Darcy did when he developed matrix microseeding, he's not on this paper, is say, well, actually, this is almost a crystal. To borrow a phrase from Henry, these are very easy to get. Actually, these are difficult to get. If we were to put these as small volumes into those, we may be able to persuade crystals to grow. But to do this, we then go from a 400 screen into a 400 squared screen. And the space becomes too large for a single researcher to do automatically in any reliable manner. So a cross-screening, where the result of each crystallization screening is fired back into crystallization screen, I think can do this on a global level. And that will be really exciting to do. So there's a suggestion for our talk later. Okay? No one's done that yet. But that would expand our space from 400 to, what's 400 squared? Big. I think we'd have large chances of getting those recalcitrant proteins to crystallize. The second thing that's done, and has also not been followed up since 2010, and I think this is genius, this is clever, okay, is this idea of using this kind of technology to develop standing waves in a solution and use this to modulate how proteins concentrate in a bulk solvent. And then what they've done with this in insulin and lysozyme, easy cases, is show that the metastable zone for crystal growth can expand significantly. So again, this is a way to get those difficult proteins to crystallize more robustly. And that's something that I'd also like to see followed up in the future. Okay? The other way, and this has been alluded to, the acoustic dispensing has impacted high throughput crystallography, is shown essentially in the X-Chem beam-line diamond, has been pioneered to extent by my PhD supervisor, Professor Sir Tom Leon Blundell, FRS FNFK, probably more letters after his name since then, when he developed his Aztecs company and sold that for 900 million euros 10 years ago or so. Their idea was that you can address this complexity of finding initial starting points. And this is one of the things that was kind of talked about this morning, but not really discussed. Where do you start your evolutionary process? Well, you start your evolutionary process with something you can show binds, whether it's by X-ray, or DSF, or SPR, or patch clamp, or fret, or whatever. Yeah? But we're talking about a large chemical space, and Dina showed us this, 10 to the 16th. Okay? So our chances of finding a good binder that's detectable easily in the first screen is 0. Yeah? It's 1,536 in 10 to the 60. This is 0. Yeah? Our chances improve if our detection methods can pick up weak or medium strength binders. So binders in this case are classified as things in the single digit millimolar, high digit micromolar binder. And for those, your 10 to the 60 suddenly becomes a lot smaller, and you have a good shot at picking these out. And what's been found on numerous synchrotron sources worldwide is that you can find these really weak binders in crystallography better than you can by any other method. Because we deal with the solid state. Crystals are grown, high concentrations of compounds are in there, put the two together and ask the question, do you see anything that's bound? Yeah? Frank van Delft, I should mention another PhD student at TLB, and here you might start to see a connection, has shown this in the Panda software by saying if you take multiple averages of individual crystals, please note not serial crystals because that's a disaster, but individual data sets, when you average those electron density maps, you can find these weak binders far more easily. And then when you measure these have double-digit millimolar affinity. They do bind, they're very weak, you may not find them by anything else, but this picks them out, solid-state physics. Okay? And Tom has done this in cocktail soaks where he puts multiple compounds into the crystal, and here you're trying to find which one it is. So again, serial crystallography is not your answer. You need the best density when you do this. And of course, reproducibility. This has resulted in many papers for Frank. As we heard this morning, XChem beamline is getting a second echo to do these. And they give a precise volume dispensation without pipetting, which is critical in this case. It allowed a lot of possibilities in new science to be done here, some of which is very cool. So when you transfer your sample as a postdoc or a PhD student in my group, plate, pipette, gone. You have no accuracy, forget about it. Certainly not when you're doing 1,536. This system allows you to start playing with, where do I start my soaking parameters? How do I start my soaking parameters? Can I control my soaking parameters in ways that a single PhD postdoc cannot do? Leading you to some very interesting soaking ideas and a whole new way to look at how you do fragment soaking into a drop. You can also start to ask questions on, because you can do this quickly enough to access large amounts of data, you can ask questions about how my crystals survive the soaking process. What are generalized soaking parameters? This is a question in the field. I don't know. Nobody knows, but we're starting to know. We're starting to find out. And it looks like 20 millimolar 1 hour, that's about where you want to be. If you'd asked me that a year ago, I would have said, no idea. Do it, try it. Now we have 30,000 data points to work from. That's good statistics. We can also do interesting things like set up gradients with concentrations at certain points and how that fusion impacts the crystal. So you can see here the starter with gradient set up. So here I think things are very powerful. By playing with that, and I come back to this, it essentially improves the detection of your weak and medium binders, which I would propose is the key starting point for what crystallography can offer to an initial drug discovery project. How do you go into that 10 to the 60 and pull out that subset that are interesting starting points? Okay? What you get out of this is binding positions, and please, these slides are a lot better online. A lot better online. But you also see the modes in which they bind, which can provide valuable information for further incremental development by genetic algorithms or other mechanisms. You see how they bind. Okay? But this leads us to the problem, and this is something, a bit of a plug for me, or for my proposal, which is how you robustly generate this data. Now I know XChem, I know Frank van Delft, I know Diamond, I was an Oxford graduate, am an Oxford graduate, and I know how busy they are there. So there is a call for fragment-based services Europe-wide, just based on the numbers. I think XChem was 11 times oversubscribed in the last run. Okay? So what we have proposed to do is take this a step further. This was an H2020 FET application. It failed. It got that close. But 99.5% of all these applications failed. So I'm in good company here. Our idea here was to couple what Alex does with MCR, what you can already demonstrably do with fragment screening, and essentially perform MCR on the results of fragment screening at the beamline. So the idea there is to cycle this and then do the MCR and put those compounds back into the X-rays, solve the structure and run around this circle as fast as you can. Okay? We originally suggested that we would borrow some ideas from Henry, who was a co-proposer on this application. Although I didn't like his liquid jet idea, I much preferred the idea of Heyman, who's his postdoc, of actually generating little droplets within oil solutions and using those to encompass individual crystals, where we could then control the microenvironment and pass these across. This, however, can adequately be done, or perfectly well be done, with acoustic dispensing in the same way. These are little images we generated of small light-life crystals. Again, go online, you'll see little crystals in each drop. And beautifully, these little pearls do not mix. They're each individual, addressable microenvironments, which I think is really cool. This will be one array, as it were, and you can imagine this is scaled up and down by different compounds and different concentrations, etc., etc., etc. Pass these through a beam, zero crystallography, if you have to. That's a proposal we're building with Daisy. There'll be a meeting sometime later this year, spring, where I'll hope to introduce this more and develop some industrial ideas or industrial interest in this as a concept. And some of you here will be invited. Proof of principle experiments were supported by Daisy. This is what we did in December. You can't see that. You can if you go there. This is all the data sets we collected manually. We took the Tom and cocktail approach, did 150 soaks for 3 biomedically relevant proteins, and unsurprisingly, what you see is fragments. This has been done enough times by other people. We get fragments. This is a malarial target we've just validated in vivo trials. This is a virus target, and this is actually a pesticide or tubercular target. And in each case, we now have interesting lead points. Big shot, fragment-based drug design kind of works. We knew this. The next step is, of course, going through the NCR reactions to try and then elaborate these molecules in a fast way and show that we can get to good compounds faster. So, sorry for that very fast-paced introduction. I'm trying to make up some time. Here is where I think we can go in the context of this perspective proposal, or if this proposal turns into a FEC proposal, a la the one we tried already. So there are 4 ways we can integrate high-throughput crystallography into drug discovery based on acoustic dispensing. The first, as I've tried to push, and I believe this is easy, this is low-hanging fruit, this is achievable tomorrow. Yeah, I just need 4 million euros, so if you're happy to contribute, I can build this. Yeah, I will take a check. So as part of an initial fragment screening campaign to generate that initial data, I'm almost 100% sure, or as sure as I can be, that anything that crystallizes, we will find fragments for. And that can be used as a starting point for then downstream development. You can then imagine, so I said that's plug and play, that will work tomorrow. It's a standard approach, it's been implemented at various synchrotron sources, and we will find things. Okay, that's a given. And the second is, you can also integrate it as a checkpoint as you go through the genetic algorithm that Alex has proposed to demonstrate your binding modes are correct. Yeah? To show that your developments are going in the right direction. You're not suddenly starting to go and hit the wrong site of the protein or do unusual things as a checkpoint. In that case, this goes back to my question that Richard answered to the chap from Waters who's sitting there. We share nationality and facial hair. It's good on 2 things. Which is how we move these reactions from these tiny volumes back into a place where you can put them back on crystals. Yeah? So what the minimum, maximum volumes we can play with to do this kind of thing. That would require some development, and I'm glad you agreed, because otherwise I would have had to change this slide. I hate doing that. And one key thing here is that, and this was asked I think from over here in the morning, is how you can ensure that your reaction results, you can pick out your binders from. We can't really show you the data because it's only just been collected at XChem, but I can tell you, you'll have to trust me, that a whole bunch of MCR star reactions were given to crystals. The crystals survived the conditions. Okay? The presence of binders, I can say nothing at this point. Okay? What I can definitely show you in the next slides is that when we do a DSF analysis, we can pick out the binders from these crude mixtures. And this is a point I cannot make strongly enough. Yeah? You don't need to do the work. These systems do not need further cleanup. They are active enough to pull out your tight binders directly. Yeah? Even in dirty systems. So here we have a titration series performed by my now very exhausted Chinese student, who's enjoying Chinese New Year, because he worked very hard, showing that this very high binder for the median MNL interaction is detectable at very low levels. These are 300 nanoliter mimicking experiments on purified purified compounds. So he mimicked 100% yield out of NCR in an echo-based dispensing, put this into the protein system, asked it to unfold, and then could find conditions where you can see changes to the folding pattern of this type binder. And this is a nanomolar binder, okay, just for full disclosure. As you go down in concentration, or as you go up in concentration of compound, you start to get non-linear effects. So you know roughly where it needs to be. And when you really over-titrate it, it becomes a mess, but that's worth knowing. What was beautiful to see is when you go to the same concentrations in the unpurified reaction mixture, no workup, that you see exactly the same behavior. You can pull this out. Okay? No workup required. Now, this is one example. One. Yeah? But these reaction conditions do not damage AN protein. Proteins are made out of 20 amino acids. If they don't damage this one, there's probably at least a subset of proteins, else it will survive. And my belief is by playing with these kinds of data, you will identify reaction conditions that are minimally perturbing, and I can hear Heisenberg rotating in his grave, to a protein system, and allow you to screen things very rapidly. Okay? No workup. That's the key thing to take back when you discuss this in your home labs. No purification required. Can find it very easily. In the volumes and masses that are commensurate with 2.5 plus 2.5 plus 2.5 plus 2.5 nanoliters, hence my question. So, the third place we could envisage this would be as a fully integrated step after binding detection. So not doing individual checkpoints or confirmed binders, but then a subset thereof. Yeah? So you find 10 binders, you do one crystal structure. Here, you could do it to do every single binder. So everything you find by iterative cycles can be addressed to the crystals, and this will provide even more information for your optimization downstream. This requires much more transportation of samples, order of magnitude more, okay? The DSF still works, so we're pretty confident that can work. However, this last point in my head is non-negotiable. If we're starting to look at hundreds of crystals being collected for each cycle, to do this even here, where our nearest synchrotron is 2.5 hours away, is non-optimal. This needs to be done within 25 meters of the photons. Otherwise, you're wasting your time. Okay? There are various ways that can be built. Parasitic modes, dedicated beamlines, these are conversations we need to have later. Okay? But doing this anywhere more than a couple of hours on mainline, you're wasting your time. And by and large, this can be confirmed by other people, but the experimental opportunities at synchrotron sources are seen by those infrastructures. They tend to make space available for new technologies. We're talking big amounts of space. Synchrotrons are big machines. Okay? The fourth, this is blue sky. So feel free to shoot me down for this one. We don't have to think about doing high throughput for confirmation or every single step. We can start thinking about doing high throughput on every damn reaction. Yeah? The XFEL, currently operating in Hamburg, has a refresh rate of 5 megahertz. That's a set of photons sufficient to collect high-resolution data every 200,000th of a second. No, more. I forget. There's 5 million pulses a second. Okay? If there is a way, without starting to accelerate the crystals to relativistic velocities, to get those samples through the beam, given the calculations from Henry Chapman of around about 250 orientations being necessary to collect a complete data set, then you're collecting thousands of data sets a second. Thousands. This is in the future. Yeah, you've got to bring it there first, but this is possible, physically. Okay? For this, I think it's fair to say we need to have major method developments, major investments by governmental or EU agencies to start accelerating these things to that rate. But it's possible then to do this kind of approach on every single sample. Okay? This is also based on the idea that there's just a physical throughput of samples means you can't consider this to be done on a synchrotron. It would have to be done on a laser source. This, to reiterate, this tomorrow, yeah, 4 million euros, I will do this for you. Okay, and you'll see the results inside 18 months. Here, yeah, pretty sure that will work. Interesting. Could be done, but that will take about 3 to 5 years to really see if it will give the kind of results I hope it will. And that's a 10-year project. Yeah? 10 years. Oh, I like that word. So, here's my outlook. Acoustic dispensing is here to stay in fragment-based screening. I think that's a given. Okay, the results that are coming in Mexico are huge. Okay, I'm a firm believer in this. It's 95% the reason why I wanted to work with Alex in this field. Okay, the major strength for me, feel free to argue, is fragment detection. Weak fragment detection. That's what it does do. That's what it brings to the table. Better than anything else. Better than MST. Better than anything else. And the fact that without workup, we can pull these things out on a DSF basis and come back in 6 months and I'll prove we can do it on crystals too, yeah, is extremely interesting. No workup required. That's the dream. Let's just screen this stuff in my mind. And true integration, I would argue, needs to be thought about being done at a photon source. Because these are the truly expensive machines. The perspective proposal is 4 million. Yeah? My FET proposal was 4 million. To build a new synchrotron to get these kinds of photons or an FEL is more than this by 2 or 3 orders of magnitude. Okay? So let's do it where we can. As a physicist, this has been my guiding principle. That if you look at things in a different direction to other people, as done by Henry, as done by other people, you will often identify really big things just by looking at stuff in a different way. Okay? However, when you do this, as Henry did, the community will often see this as a risky approach. Okay? Sorry. However, the community will often see this as a risky approach. Okay? People will say you're daft, it can never work, this is dangerous, your career will take a nosedive, the tiger will bite your face off. But the reality, oh damn, that works all right. Where is it? There. The reality is sometimes great things happen. And this is one of the biggest moments in my entire life. Putting my ear on this animal's chest and hearing him purr is something that I remember from 6 years ago. That was awesome. Okay? At this point, I hope I've made up some time, and I'll take any questions. And the previous question, yes, these slides are available already. Feel free to distribute them as you see fit. Did it work?
Yeah.
You were on your smartphone, so you were either Facebooking or you were checking. It worked. Now I'm chairing this bit, so I can ask myself questions, but that would seem a touch arrogant. Okay. What do you need? Can I just end this? I've not met how, but he's here to talk about how the acoustic dispensing has made an impact on his research.
Yeah, thank you. So what I like so much about this proposal, this discovery at the speed of sound, is my lab is sort of experimenting a little bit with all the different aspects. So my lab has a lot of high throughput screening. We also try to do library synthesis using acoustic dispensing, and we're also experimenting a little bit with parallel crystallography and fragment soaking, collaborating with Frank van Delft. And I'd like to explain a little bit what it is that we do in my lab at Leiden University Medical Center. So we are using chemistry to try to understand biology. And about half of the people in my lab are hardcore organic chemists, doing small molecule work. we have a few peptide chemists that synthesize peptides, proteins, etc. About 7,000 a year, and the rest of the people in the lab do biology. And doing this, this is what we study in my lab. So we study how proteins are targeted for degradation by a post-translational modification called ubiquitin. And this targets these modified proteins to the proteasome, which is a cellular machine that shreds targeted proteins for destruction to produce polypeptide fragments. And these fragments, they are then in the ER, in the cell, loaded into so-called MHC class 1 complexes that are moved to the cell surface, where these peptide-loaded complexes show their cargo to the immune system, and the immune system can then respond, and upon recognition of these presented peptides by T cells, T cells will directly kill the antigen-presenting cells. So basically, if this chicken represents a viral protein or a tumor protein, then through this cellular pathway, our body, our cells can indicate cancer or infection to the immune system and counteract by killing this cell. So this is a very key component of our immune system, and ultimately this is something that in my lab we like to exploit for drug discovery. So it's a defense system that's already there. Sometimes you like to turn the system on to make it work harder in case of cancer, or you want to tune it down in case of autoimmune diseases, for example. And this is the reason we are investing this, and what we are using chemistry to do this. And we would like to modulate study individual events within this pathway. What I will first explain a little bit is about ubiquitination. This is a modification that's very comparable conceptually to phosphorylation. Phosphorylation is a process very well understood. All of you have heard about it. And we've been studying it for many years, and as a result of that, we've been able to develop drugs, and there's a large number of kinase inhibitors now in use in the clinic that have a clear effect on human well-being. Another modification is ubiquitin. It's conceptually similar to phosphorylation. The main difference is that this modification, it's not as well understood. So, and why is that? Well, I've drawn the phosphate group here in perspective to the ubiquitin molecule. Clearly, these are different. Ubiquitin molecule is much larger. It's difficult to make. We don't have good assay reagents, etc. Basically, the complexity of this modification makes it more difficult. To make things even more difficult, ubiquitin is normally linked to the C-terminus onto amino residue of another protein. It can also link to itself, to any of its lysine residues, to give rise to ubiquitin chains. And these chains, they physically look different. So the way ubiquitin is introduced is by means of a pathway involving E1, E2, and E3 enzymes. They need specific combinations, and very often we don't know the combinations needed required for ubiquitination of a specific protein. And then there's about 100 proteases that can remove this modification. And the important point I like to make is that almost all of the enzymes involved in this pathway act through cysteine catalysis. And cysteine catalysis is something that's notoriously difficult, especially when it comes to high throughput screening, and campaigns are, you normally see a lot of artifacts due to, for example, redox sampling effects. So the chains that I told you about physically look really different, and they're involved in all kinds of different cellular events they trigger, including protein breakdown. So my lab has been studying the system for the last 15 years or so, next to other biochemical questions. We've been building a specific toolbox to study this, basically to make the toolbox that allows us to study the ubiquitin system, to make it look like the one that we have available to study phosphorylation. And and because the ubiquitin system is so complex and all the catalysis is so difficult, I think it's very important to come up with better assay and screening technologies, basically, because it's something that currently remains difficult. So in order to get there in my lab, we try to combine biochemistry with chemistry, because the two disciplines normally talk sort of a bit of a different language, and they need to learn to understand each other to give a useful application also to novel technologies that chemists develop to eventually come to better findings. So just a quick example of some of the things that we developed in the lab. Over the last years, we developed methods to that allow us to incorporate very specific building blocks, such as this thiolysine building block in any peptide of choice. And this basically allows us to take advantage of a technique called native chemical ligation to react ubiquitin thiol esters with this thiolysine residue to here end up with ubiquitinated peptides and proteins. And then after desulfurization, we end up with native ubiquitinated peptides and proteins, basically, and this allows us to make all the assay reagents needed to study this specific system. So we can, in the lab, synthesize ubiquitin proteins as well, and this allows us to make very complex assay substrates. So in order to measure the activity of, for example, the deubiquitinating enzyme, you need substrates, and this is a case of a fluorogenic AMC substrate that releases a fluorogenic signal that provides a typical readout in a plate reader using more traditional screening methods. This is how we make it, and just to give an example of how important assay reagents are, here you see an assay where we use a deubiquitinating enzyme that we assay against ubiquitin AMC, and as you can see, there's almost no signal. This assay reagent that contains a true peptide linkage, also no signal. And here you see what it looks like if we incorporate some polypeptide context in the substrate, and now you see incredible activity for this enzyme. And this will, of course, determine the success of your of a screening campaign, as it gives you a bigger assay window and it makes everything more reliable. So I think it's very important to invest in good assay reagents, assay technologies as well, especially when working with sort of notorious enzymes that are difficult to address. So I think traditional screening libraries, together with Professor Dilding, I've been involved in the European Lead Factory. We've been synthesizing, together with some SMEs, a collection of 200,000 sp3-rich purified molecules. I think such sets are very important to have. This is a unique set, I think, but it will, such sets are very useful when screening, I think, probably against easier to handle targets, but targets that are notoriously difficult to address. I think it's having our capacity to do chemistry on demand will become very important, at least in my opinion. We work also on some validation technologies, and I love to use a lot of activity-based probes. Those are elements that contain, those probes that contain a recognition element, a readout, a label like a fluorescent dye, and a reactive moiety that can specifically react with enzymes in an activity-based manner. And this can happen in very complex samples. I'll give you an example of what that allows you to do. Here you see, for example, a probe for deaminating enzymes, and the probe is tagged, and here you see different reactive groups. These reactive groups that can covalently react with active site cysteine nucleophiles of these enzymes, and you can visualize the products of the reaction with these enzymes. So these are experiments carried out in cell lysates, and any cell lysate can contain up to 100 of these enzymes. And the advantage of this technique is that it allows you to follow the activity of this entire family of enzymes in a single go. And this allows you, for example, to look at selectivity of inhibitors. Here you see an example of a covalent inhibitor of a family member of this enzyme, and it's fully selective for this bacteria, as we can compete it away. So clearly it is possible to make molecules for this family of enzymes. It is just very hard. So over the years we've carried out many treatment screens. We did a lot of them within the European Lead Factory, also a few in collaboration with the Pivot Park Screening Center, and some very large ones in collaboration with companies. Over the years we've done dozens of smaller screens in my own lab using traditional pipetting. But since about a year or so, we have our own acoustic dispensing-based screening station. We're now finishing our first really big screens with just over 100,000 molecules. And this makes us very flexible. Recently, we also started using this acoustic-based technology to start doing some follow-up optimization chemistry. And what we notice is that and we are successful in that, doing both the chemistry and the in situ testing, and we get good results. But what we also noticed is that there's not much known about synthesis using acoustic dispensing in literature, and it needs a lot of optimization. And I think it will be super useful to have some general protocols available that you can use to sort of translate traditional chemistry to these machines. And at least in my opinion, especially for super notorious difficult targets, the future is probably not in screening enormous standard sets of molecules, relying on smarter fragments, smarter molecules, and our ability to rapidly optimize and synthesize things by synthesis. So I think a lot will come in the future in this area, especially considering technologies as this parallel X-ray technology. So a few examples of what we use this equipment for in the lab, and yeah, it's really pretty funny. All the just PhD students in the lab, they just walk around with 384 well plates, and you know, when I did my postdoc, I walked around with these racks with single Eppendorf tubes, and things dramatically changed. Yeah, we use a machine for all kinds of completely automated protocols, and the results have become so much more reliable, and sometimes this matters a lot. So here you see an example of a very typical IC50 curve that a student would make in the lab doing manual pipetting. This is what it looks like if they run a standard protocol using the acoustic dispenser, and you can do many IC50 curves, and this takes hours, and this probably take weeks if you do many. So yeah, and I'm sure there's many other applications for this equipment. We only recently started with the synthesis part. Of course, you do the standard screening. Yeah, and this is yeah, and the synthesis, that's what we are currently looking into. But this, I think, this looks very promising. So I think there's a big future ahead of us, and I think this consortium yeah, will make this move forward. Thank you.
Thank you. Are there any questions to the audience as I move to the front? Can I start by asking, you alluded to smart molecule solutions rather than coarse high throughput approaches.
Yeah, so with smart molecules, I mean things like privileged molecules or covalent fragments, molecules that give you some clue in advance about what they might do.
Well, this is so designed on a protein by protein class.
Yes, yes.
So phosphatases you go in a certain way, kinase in a different way, and then cysteine proteases in a third way.
Yes, and if you have, if your target protein contains a class of nucleophile, you need to match those with a certain type of electrophile in your molecule. I think it's about being smart and good matching. Our approach is like fragment growing, that may also help a lot.
What about amounts that we're talking about? So when you're showing the fragments and their cellular or the lysate activity, are these compatible with the nanoliter approaches, or will you need larger volumes? Well, massive compounds.
That's a good one. I have to get. I mean, this is a very old-fashioned plot, but I think this is more important for the follow-up chemistry to follow selectivity of molecules. But also for this, ultimately, you want to have higher throughput methods, I would say.
So there's an argument of having acoustic technology developing along with the detection method.
Yeah, and I think that is the way we should go.
If not, thank you very much. Well, Christian's setting up. Can I use it? Yes, I think you can. So while Christian's setting up, I can introduce him, hopefully enough. And this will go on to, yeah, exactly. So Christian is here representing Nanotemper, who kindly helped pay for some of the lunch you enjoyed.
For the dinner, I think.
For the dinner?
For the dinner.
Okay, so the dinner will be even better. And he's representing Nanotemper, who have some very cute technology that wasn't available for these until recently. And I think it's perfectly situated to look at thousands of experiments a day. We're okay?
Yeah, I will do that manually. So. Okay, perfect. Thanks, Matthew, for the kind introduction. Just to let you guys know that we are in close contact with Matthew and Alexander's group since years already, because they already apply our methods to measure the affinities of the compounds against the target proteins since a while already, but in a manual way. And today, everything is about increasing the throughput and measuring as much as possible in a short time course. So, my talk will also introduce Alexander's and Matthew's group and all of you, hopefully, to completely automated affinity screenings based on microscale thermophoresis. So, the match to a program that is called Drug Discovery at the Speed of Sound is perfect, I would say. So, that should work like this. Is it me? That one? Yeah, I found it. So, microscale thermophoresis, some of you might not have heard about it, is something that is orthogonal to SPR or to ITC. So it allows you to study affinities. But the difference being that there is no immobilization of the target protein with towards a gold chip, let it be, or you don't have to work with super high concentrations. That's why we think, and also in Alexander's group, that the match of implementing microscale thermophoresis in the drug discovery process with many, many different molecules is the way to go. And the phenomenon of thermophoresis is actually much, much older than SPR. It was discovered independently by Carl Ludwig and Charles Sauret back in the 19th century with very, very basic experiments that they did. But nothing was made out of it until back in 2008 in Munich. Two PhD students, they stumbled upon these old publications and realized that now with modern microscopes and confocal setups and single molecule detection levels, that thermophoresis is a principle that applies to any biomolecule, let it be a protein, a DNA molecule, an ion, anything. So manual instruments were introduced first, and here you see a picture of the instrument running in Alexander's and Matthew's lab, where the student has to pilot everything and load everything by hand. But I will focus today on the automated solution. And just to let you know, we have seen already many, many data from Monolith in the morning during the talks, and Matthew showed also a big data set that was obtained with Prometheus at the Hamburg site at DESI. So all of this can be fully automated. I will focus on the microscale thermophoresis as mentioned for high throughput screenings, and I will give a short introduction to those of you that don't know about this biophysical method. What is the difference towards, I would say, more established things like SPR or ITC? Then how we see the implementation in a high throughput way, that you, for example, do single point screenings first to get rid of the very, very weak or non-binders, molecules that simply don't address the binding pocket. And then with those where you show they do bind, go into the affinity screening, then give this data back basically to these genetic algorithms to, in the next generation approach, improve the affinity. And to create a little bit of trust, I think I will, the decision was that I also show 3 different types of screenings, just briefly, that were carried out by Sanofi or by us or by Vernalis against 3 relatively well-known targets for drug discovery. So you see here how the instrument looks like. Here is implemented next to a liquid handler. So we are 2 or 3 steps after all this echo dispensing has been applied. But first about the background as mentioned. So what you will see here in the video is basically thermophoresis in real time. We have here the label DNA swimming around in solution in an Eppendorf tube or somewhere. And now a infrared laser is focused into the solution and slightly and locally warming the solution. And what happens now is this DNA diffuses away. And that is positive thermophoresis. And this is what DNA does. This is what a protein does. This is what ions do when you apply a temperature gradient. Okay, it might look nice or not, but what are the factors that influence the direction and the degree and the strength of thermophoresis? So this all is described finally by the Soray coefficient. Soray being the guy in the 19th century that spent his whole academic career on describing the phenomenon. So, but then it was finally done to extract all the factors contributing to it. And in this Soray coefficient you see that the size of a molecule or a particle plays a role. Also the charge to the square. So changes in charge, for example, DNA binding to a protein, have a dramatic influence on the Soray coefficient. And interestingly, and this is why it comes into play when you would apply it for fragment-based lead discovery, for example. Also changes in the hydration shell influence the Soray coefficient. Or in other words, the solvation entropy that changes due to molecular rearrangements. Now this basically means whenever one of these 3 parameters changes, we see the difference compared to the target protein alone. We see when something is binding. And if you do a titration experiment, you can extract a KD out of this very, very quickly. And since it is a fluorescent-based method, this basically means that everything is free in solution, diffusing freely, no immobilization is required. And with fluorescence detection, you work with very, very low amounts of samples. So we speak here of up to 3 microliters of picomolar to nanomolar target protein concentration. So the perfect fit if you want to measure as much as possible. Interestingly, the instruments are never in touch with the sample, so it also allows you to work with any type of detergent or whatever comes to your mind, hazardous substances. And this also means that since there is no liquid handling can break or clog, which is also relatively important if you're aiming for high throughput. So the setup to extract affinities in just a few seconds is that you have the target protein fluorescently labeled, site-specific, 1 dye or less than 1 dye per protein, so we don't want to block binding sites. And then you have a serial dilution of the ligand of the compounds. And so the protein constant, the ligands at decreasing concentrations. Now the microscope, the instrument, scans any of the capillaries step by step. It goes through them, like 5 to 10% measurement time per capillary for an automated system. And the infrared laser is focused into the solution and locally increasing the temperature by around 2.5 to 3 Kelvin. So it's important to understand that no protein is being boiled. And on the next slide you see, or maybe I use the whiteboard, no one has used it yet, except Matthew, to write down his URL. Let me see how we can do that. Probably you don't want to draw molecules and the structure. So my drawing is more basic, so it is basically a drawing of these initial experiments back in the 19th century when thermophoresis was discovered, but I think it explains it quite nicely. That what they did, those scientists, they connected 2 Erlenmeyer columns to each other. So this one stands a little bit lower, not out of purpose, but of my drawing skills. And inside here is a salt solution, sodium chloride. Now the one is being boiled all the time with a Bunsen pan, and the other one is kept in ice all the time, so cold. And the distance here is around 1 meter of this glass pipe. So now there is a temperature gradient. This gradient was kept constant for 3 weeks. And then all of that was suddenly disconnected. And there was a measurable difference in ionic concentration in between those two tanks. Guess where the concentration was higher? In the cold Erlenmeyer column. Positive thermophoresis ions moved to there. Now we go back to microscale thermophoresis, how it is done today. There's no Erlenmeyer column, no big liter volumina of the molecules of interest. You see here a picture, a confocal image of a temperature sensitive dye, ECF. And here is the infrared laser that we use. And you see that there is a temperature increase of around 3 Kelvin, as I mentioned, on a 20 micrometer length scale. So this means you have 1 Kelvin per 10 micrometer corresponding to 1000 Kelvin on a centimeter length scale. So the temperature gradient that we apply in total is small, but ultra steep. And this is why you don't have to wait 3 weeks to have a measurable difference, only a few seconds to see a difference from an unbound to a bound state. And if you now plot basically what is happening here, if you monitor the fluorescence and the movement of molecules and plot them, you see that there is an initial state, the infrared laser is turned on, and then thermophoresis starts appearing. Quite simple. But how are affinities being measured? You do the same experiment now for example, 3 different or 8 different compound concentrations, if you want to have a precise KD. Now you measure the thermophoresis for any of these ligand concentrations, protein, target protein, always constant, and you plot them as a function of the ligand concentration. And when you get to the bound state, thermophoresis is different, because there might be a change in mass or in charge or a conformational rearrangement. Whatever triggers, whatever is induced by the binding, changes the thermophoretic behavior of the target protein. And now you calculate the ratios, of course the software does that for you, and plot them as a function of ligand concentration, apply, for example, law of mass action model or Hill equation, whatever you want to extract. And for example, in this case, determine the KD precisely. Now for single point screening, it's quite straightforward. You measure the target protein alone, you measure all of the compounds that you synthesized at fixed concentrations, and you simply identify the binders. So these are not the binders, but those here, they could be potential binders. And in the second step, you go now for those molecules, those compounds, to the affinity screen. And here it is important to understand that you need around 80 seconds of measurement time to precisely measure a KD on the automated system. And this is how we would actually see the workflow. That these ligand stocks coming from the multi-component reactions are prepared, for example, in 384 well plates. Then they are diluted down, for example, automatically with a Hamilton robot. We always work together with Hamilton. So then those ligands are diluted and automatically loaded into the instrument. It carries out a single dose response screen first, automatically identifies the binders, the hits, and then in the next step, of course, there are only green and yellow molecules that went through the quality check, so meaning that they are there, as we've seen in the talk in the morning. So you make the hit selection based on this. With the hits, you go into the affinity screening, and the software automatically makes a KD ranking of all the compounds that you measured. This software looks like this. So you see all of the, you could see it if you would have a better projector. But you see the controls here, for example, the DMSO control, and you see the potential binders and duplicates. You see them being ranked according to the affinity. But what you also see, and that is quite interesting, so this is, no, it comes on the next slide. But you also get quality checks. For example, did a compound induce aggregation of the target protein? That can be a problem. Or is it sticking to surfaces? So are you only seeing apparent concentrations? And I would like to end the presentation by showing you a little bit of data. For example, published data in applied biophysics and drug discovery, relatively new, where you get a really detailed insight in what is being done. Here, small molecules against the p38 alpha, the active form of p38 that is involved in inflammatory responses and diseases. So basically inhibitors that were screened first for the hits and then for the affinities. You see, for example, something that was considered a potential binder in an affinity experiment did not show a dose response curve at all, but the binders here that were identified had different affinities. And this is the take-home message here, that the amplitude of the binders does not correlate with the affinity at all. That has nothing to say. That only tells you that it seems to bind and alter the thermophoretic behavior of the target protein. So you get quite different KDs along those hits here. So the affinity screening is important. Data from Vernalis in collaboration with Vernalis against HSP90 protein. Also, very well elaborated target. And I would like to end the examples with a unique intrinsic quality control feature of microscale thermophoresis, that it is able to detect aggregation. So for example, protein can be aggregated from the start, but this is what you typically try to avoid. But also compound can induce aggregation. And normally, we have seen traces. Here, for example, you get clean traces for single proteins diffusing. But when a compound induces aggregation, you get these irregular MST traces. Easy to understand that big chunks of protein swim through the detection volume. And the software automatically detects those aggregators and highlights them. So be careful here with this molecule. Interestingly, this was done by Sanofi, when they correlate the MST experiments to their SPR measurements, those compounds that induced aggregation were ranked among the best in the affinity range of the SPR experiments. But that is simply, these are false positives. You don't want something that induces aggregation. Yeah, so you basically see that here, that you can easily correlate the DSF, temperature shift experiments with MST experiments, and also the ones that induce a large shift due to binding are the ones that are also easily identifiable with microscale thermophoresis. The ones that induce protein aggregation, they were also ranked relatively high here. So what you get there are false positives. The technology is applied now basically from every big pharmaceutical company, also from, we have people here from, for example, from AstraZeneca. So you have colleagues that are already experienced in it. My last slide is basically, I hope that the take-home message for you is that you get very, very fast KDs, that you only need a little bit of target protein. For example, here 100 picogram of target protein of MEK1 kinase to screen 200 compounds in the case of Sanofi's reference application. For the biologists or the med chemists, it's relatively interesting that you have close to native conditions. You're not immobilizing anything, you're not working at super high concentrations, you can work in lysates and serum and plasma, whatever comes to your mind. No liquid handling means nothing gets clogged, nothing breaks. The instrument can run for like 3 days in a row if you need. And in the case here of the drug discovery group in Groningen, I think that is something that should not be underestimated. They are doing this biophysical analysis already since years, meaning they have publications, they did the proof of concept study as we've seen in the morning. The assay development, everything is in the hand already. It's just the next step to bring it to a higher level of research. And with automation, I think for me, it's kind of fascinating to see those robots work. Let's see if the video works. Yes, it does. Wow. I wanted to show you to get a picture and understanding how it looks like. Just quickly, here's the video. As mentioned, we work together with Hamilton. They are really, really good when it comes to liquid handling systems. Everything is prepared automatically in 384 format. All this is being cooled if you have to guarantee the activity of the target protein, if it is temperature sensitive, for example. All that is in a completely controlled environment. Here you see the loading of the samples into the glass capillaries. Then they are transferred to the instrument. And it starts measuring. Gives you the KDs, gives you all of the data automatically, ranks them if you want, and it shows you high affinity binders. Thanks for the attention, and please feel free to ask questions. Thank you.
So, thank you, Christian. Are there any questions from the audience before I jump in? Yes.
So a step here is to label your protein, right?
Exactly.
But because labeling also has some efficiency, right? It's never 100%. So it will be, let's say, 90% in a good day. But at the end, you will test only the labeled material, right? Am I getting it right? So if you have a mixture of a sample which is 90% labeled molecule and 10% unlabeled, you will see only the labeled one.
Yeah. That is actually, good question. It is a positive thing. You're totally right, you have a labeling efficiency. You can easily measure the degree of labeling that you achieve after the labeling reaction. That is not a problem, you can do that with a UV spectrometer. But you're right, for example, if you're targeting lysines and you have 20 different lysines, you have a statistical distribution of one dye at one of those 20 different labeling sites that are potentially accessible. And this means, for example, that one of the lysines might be close to the binding pocket, interfering with the binding, but 19 other fractions are still active. So that's actually a good thing. If you want to control specifically the labeling site, one can, people, for example, introduce unnatural amino acids and then per click chemistry. You can go for, if the histidine tag is still present, you can label that. Intrinsic protein fluorescence is an option, even though being not as sensitive as, of course, fluorescence. There are many, many different ways, and it is important that you do a detailed assay development beforehand, make sure that the protein is active, that nothing interferes, and then go for the screening.
I have a very quick and simple question. So the
Oh, yeah.
labeling you only need for detection, right? Not for the effect.
Exactly. Yeah. Therefore, intrinsic protein fluorescence is awesome.
Maybe another question?
Of course.
Equally short. So, considering, or if you have a fixed baseline, say a cell lysate or whatever, you can work with whatever medium you want, right? So it doesn't matter if it's a mixture or whatever, you just need the baseline and then you can, in principle, detect the changes.
Exactly. Yeah. So what one can do, for example, is spike lysates with the labeled target protein, or express a fusion protein to the target protein of interest. Then there is no purification at all required. What also works is we have a non-covalent dye that, with high affinities, finds 6 histidine tags. So you can also only express a 6 his tag. Also endogenous expression that is possible with CRISPR-Cas editing, for example. They titrate in the dye into the lysate, titrate in the ligands, and do the affinity analysis in presence of those 100,000 different other proteins. Yeah. Thanks.
If I can just follow up. So the morning was talking about going for using genetic algorithms to go from free binders to tight bindings. Now, you have experience here with EMST technology. What's weak, you can pick up, and what's tight. I know every biophysical technique has an upper limit of affinity that it can reliably measure as well.
Yeah. So there are applications with millimolar affinities. The limit here is rather a solubility. I think that might hold true for compounds as well. For high affinities, I've seen, for example, 20 single-strand binding protein with an affinity of around 20 picomolar against different types of single-stranded DNA.
Okay, so you have a very broad range from weak to tight.
Exactly. The reason is that that the fluorescence is such an intense signal that we can work with very, very low target protein concentrations, so that we have nice saturation curves that don't have a kink where the concentration of the target is below or in the range of the KD. That is the prerequisite to extract also precise high affinity cases.
And a follow-up question kind of targeted at my audience here. If you could look at the future, what is the minimal sample volume you can usefully use? So what's the lower end that you can detect your bindings so that they know how much they have to move around?
Yeah, currently around 3 microliters, and that means 1.5 microliters of ligand plus 1.5 microliter of the target protein.
Okay, so this is way accessible. We're talking about somewhere from the 2.5 nanometers.
Yeah.
Are there any further questions? Okay, if not, thank you again, Christian. Thank you. And now I'd like to introduce George. You're going to have to help me for a second. I'm sorry, I'm the wrong nationality.
It's difficult.
Rodriguez?
Yes.
It's George Rodriguez. I think it's been stolen. This is Georgios. Sorry, is a homegrown researcher. He works up at the Zelica campus, so he's relatively new to this part of the city.
Yes.
And his specialty is single molecule fluorescence resonance energy transfer, FRET studies of proteins, and he will explain to us in his presentation how he envisages, using this technology within the context of a high throughput screen.
Yes. So thank you very much for the introduction. So yes, I'm Yorgos, and I'm a postdoctoral researcher at the Molecular Biophysics group at the other campus, the Session3 campus. And I'm a protein biochemist and a biophysicist, so I'm very pleased to be here today because I've been learning many new things from you, experts in drug development and design field. And what I would like to convey today is that my favorite experimental tool, which is single molecule FRET, can be very important to guide drug design and development, and also can be used as a high throughput method, so fully compatible with high speed, let's say, drug discovery. And I would like to start by stating that for a long time it has been known that protein flexibility is very important for drug discovery, and this is a review from 2003. But in a very few cases, protein flexibility is taken into account from drug discovery because it's very difficult to be determined experimentally. So in my talk, I will explain to you why protein flexibility is important for drug design, why protein flexibility can be determined accurately only with single molecule resolution tools, that protein flexibility can be an ideal marker to probe drug target interactions, and also that protein flexibility can be determined in a high throughput way using single molecule FRET. And I would like to start by showing to you a simple protein made up of two domains, the blue domain and the orange domain. And what medicinal chemists like a lot, and we have a structure of that protein which is ligand or its inhibitor, small molecule inhibitor, because in that way, medicinal chemists can identify the 16 hydrogen bonds which are represented here in this slide with the green rectangles. And by using this information, what medicinal chemists like to do is examine with very powerful computational tool this pocket to design small molecule inhibitors, and after medicinal chemists enjoying very much synthesizing these small molecule inhibitors for testing and verification. So what I would like to tell you now is that I've made a single point mutation to that protein to abolish only one of the 16 hydrogen bonds. And now I have a quiz for you. So if I would tell you that the wild type protein having 100% of the interactions has a KD of 1 micromolar for its ligand, so if the ligand would be an inhibitor, it would be a Ki of 1 micromolar. So in the mutant protein that maintains 94% of the interactions because it loses only 1 out of 16 hydrogen bonds, I would like to ask you, what do you think would be its KD or Ki now? Please raise your hands if you think that the KD would be, in that case, the same, unaltered. Okay, 1. Please raise through your hands if you think that the KD would become 5 micromolar. Okay. Raise your hands if the KD would become 100 micromolar. Okay. And 10,000 micromolar. Only. Okay. So, yes, so the correct answer is 10,000 micromolar. It has been identified only by one person. And I think this is an unexpected result because by making a mutation that abolishes only 6% of the interaction, we impact the affinity more 4 orders of magnitude. So this is really unexpected, I think, to everybody. And we found the reason of this unexpected result because we found the binding mechanism of this protein to its ligand. So this protein, in its free state, it's in an open conformation, and the binding pocket is not formed. In the first binding step, the ligand binds only to the blue domain, and the ligand is sensed only by one residue here from this other orange domain. And this interaction triggers the protein to undergo a conformational change to a closed state to form the high affinity binding pocket. And in the mutant protein that has this interaction abolished, this protein cannot go to the closed state, so the high affinity cleft cannot be formed, and you have only the low affinity cleft. And such results can be only obtained by using a very, very powerful tool, which is FRED, because FRED can be used as a nanoscopic ruler because we can measure distance changes with angstrom resolution and with millisecond to microsecond time resolution. So FRED is an ideal tool to measure protein flexibility in real time. And in that case, we can label a protein with 2 probes at specific positions. And in that situations, where the 2 probes are apart, we will have a low FRED, meaning that we will have a donor fluorophore here, but we have a very bright color, and very little energy will be transferred to an acceptor fluorophore that has a very dim color. It's not bright at all. But when the protein would undergo a conformational change, the 2 probes will come close together, and now the green fluorophore is dim, and the red fluorophore has a very bright color. And this we can measure in real time. But to measure precisely protein motions, we don't need only FRED, but we need to probe it at the single molecule level. And the reason is that with the classical ensemble FRED measurement, we'll get the information that we have here, only green apples. and we'll miss the rest output, which is very important in a lot of cases. So with single molecule tools, we can detect heterogeneity, which is very, very important. So with single molecule thread, we can detect protein motions in real time of different molecules. And what we would do with ensemble measurements is that we would average out at each time point the signal. And due to statistics, by averaging out millions of molecules, we get the same value. So we get a constant value over time, meaning that we have an immobile protein, which would be the wrong conclusion. And I would like to show only this piece of data for the system that I described to you. So in the wild type situation, you can see how nicely the protein moves between an open state and a closed state in which the domains move to form the high affinity cleft. While in the mutant protein, with the low affinity, the protein is unable to go to the closed state and form the high affinity cleft. So you get only the low affinity cleft. So I would like now to switch from this simple system, which is only a two-state model system, to a much more complicated system. And I want to say from the very beginning that this was due to my collaboration that started less than a year ago with Professor Domling. And this collaboration and support I have from his group, I think we have very nice single molecule thread results on Rust proteins, which are very, very important for cancer biology, because these are found to be mutated in more or less 30% of every type of human cancer. And I'm going to show you some of the results we have on these proteins. So also Rust proteins are hypothesized, as the example I've shown to you before, to have two states. A non-state, and in this state it has been thought that the protein has these two switches, switch 1 and switch 2. Yeah. And in the on state, these switches are attached to the rigid domain of the protein, which is this one. While in the open state, these switches will become detached from the rigid domain. And how this protein works is undergoing changes from the on to the off state, guided by GTP binding and hydrolysis events. And we wanted to test that, and this is really preliminary data we have. And I think these are unique in the Rust literature because we can probe the conformation of switch 1 and switch 2 at the single molecule level. So in these plots, that I do not have the time to go into detail, each dot that you are seeing represents one single protein. I don't have time to go into detail, but I will be very happy to discuss these results with you afterwards. But what I want to point out is that these results indicate that the protein is never in one single conformational state as hypothesized till today. So the protein in the resting state has switch 1 in an open state, an intermediate state, and a closed state with the following percentages. And these are the results for switch 1, and these are the results for switch 2. So next I have a movie in which I'm representing our results and our methodology. So as you see, if we would like to probe conformations of switch 1, we would put one probe, a donor fluorophore here, and an acceptor fluorophore sampler here, which now is very, very dim because the two fluorophores are apart, while during the movie, when the two fluorophores will come together, you will see changes in the brightness of these two probes, which is experimentally what we were really measuring in real time. I will start now the movie. I hope. for it to work. And it works also now.
I think you need to move the presentation mode.
To move,
To leave the presentation mode and then
to leave the presentation mode.
yeah, usually it works.
Okay, so I'm seeing it now here, but it's not seen over there. Yes. Okay, yes. Now as you see, that while the two probes are approaching, the green one becomes dim and the red one has a bright color. And now you will see the full intrinsic conformational transitions and the flexibility of the protein. So this is what the protein does intrinsically. And afterwards, you will see a surface representation, and you will notice that the clefts, the binding clefts, are not static, but are dynamic. So they are continuously formed and destroyed over time. And for this, please follow now the laser pointer. So here, look at this cleft and how it's not really static and dynamic, which is continuously made and destroyed all the time. And here, another part of the protein. Which does exactly the same. So, and now I can go again in the presentation mode. Okay. So what we did also, it's not that we only probed the intrinsic motions of the protein, but we probed also how these motions are changing when an inhibitor that shows in vivo efficacy by published papers in the literature, and this compound is synthesized by MCR, by the dominant group, how this impacts protein motions and protein flexibility. So for switch 1, you see that after binding of the inhibitor, the population of protein, or the time that the protein spends in the open conformation, stays the same, from 23 to 24%. The time that the protein spends in the intermediate states is decreased from 52 to 38%, and the time that the protein spends in the closed state is increased from 25 to 37%. So after binding of the inhibitor, the conformation of the protein switches to a more closed state for switch 1, while for switch 2, it has the opposite effect and switches more towards an open state. And to give you some logistics, for this measurement, it took us 5 minutes to probe binding of this compound, which means that we could test 288 compounds per day with our current microscope. And what we are also doing is that we are using the nanodisc technology, as we are using it with many other membrane proteins in the lab successfully, and now we are using it also for rats. So what these nanodiscs are, these nanodiscs are this belt protein, that this belt protein can internalize a membrane lipid environment here. And what we are doing now is that we are binding, as also others did for different reasons, we are binding RAS to these nanodiscs, and we are examining its flexibility and protein motions in its native environment, which is the physiological relevant situation, because RAS is a membrane protein, so it exerts its function at membranes. And what I would like to say, that we could convert very easily our confocal single molecule Fred microscope to a multi-spot confocal microscope to perform 8 measurements at the same time. So this means that we would be able to screen 2,300 compounds per day. And the price, the full price of such a microscope is 120 kilo euros. So, as a take-home message, I would like to point out that single molecule FRET allows to determine protein flexibility, that it's very, very important for drug design and development. It represents a novel drug screening platform because it doesn't screen only the binding event, it screens what is its repercussion on protein structure and flexibility. And this information is very, very important. It requires, because it's a single molecule method, so we are detecting single molecules, it requires very small protein concentrations, because molar concentrations are enough, and the volumes can be reduced drastically to a few microliters. And thus, I think it's fully compatible to be incorporated in drug discovery at the speed of sound platform. And I think also it can be really coupled to very nice technologies and that people presented here today. And with that, I would like to have your questions. But before that, I would really like to thank the people. So I would like to thank really Professor Donnelly for all his support and all the members of his group for our very nice collaboration. Professor Camacho, and we are trying with him to establish really powerful computational tools, not only to target static protein clefts, but dynamic ones, because that's the situation with many proteins. Ras is a signaling protein. It's a very complicated protein. It's far, so people nowadays have a very simple view of that protein having a two-state, being a two-state model, so having a non and an off state. But what we see, the situation is very, very far from that. And that's why probably this protein is undruggable till today. And also I would like to thank the US and NIH RAS initiative that provide with us the RAS genes, and we have a very nice collaboration and exchange of ideas with them. Also I would like to thank members of the molecular biophysics groups at Zerbitia that helped me a lot, especially user that helped me a lot with purifying and labeling RAS and adapt the system for single molecule investigations. And people that here with their expertise in biology, in physics, and Nick that helped me a lot with the movies. And also, personally, I would like to thank Embo and Benny for funding me these years. And you for your attention.
Thank you very much. Are there any questions from the audience? Please.
So yeah, great talk. So I'm just curious, have people looked at RAS with molecular dynamic simulations? Yeah. And if so, are the results consistent with what you observed?
To tell you the truth, I'm really new in the RAS field. I've seen those calculations. They also claim that there is flexibility, but I think it's far from this data. Because with FRET, you cannot only see different FRET states, but you can come up with real distances, right? Translate FRET values to distance values. So flexibilities, according to our experiments, seem to be really huge, even much, much bigger than what are seen in crystals. So the protein really seems to undergo changes much bigger than what you would think by seeing its structures or on crystals, even its NMR structure. And I think the issue there is, of course, it seems that the protein is really, really flexible, which gives also the reasoning why this protein, being so simple, it's only 20 kilodalton, can affect 6-7 signaling pathways and having 30 different partners. And to my view, this would be very, very difficult if it would be a simple protein having an on and an off state, right? But here we see that the protein is really, really dynamic. That would explain all this biological diversity of that protein. And so I think yes. So what our view? These are preliminary results, but the view is that the protein is really, really flexible with undergoing huge conformations. And the issue is now we have single molecular resolution tools. So all the other methods are ensemble methods. So they are, or even NMR, right? They're averaging information of thousands of molecules. But here we have the power to analyze one molecule at a time, which is really powerful. And also I think it's great that even if we analyze single molecules, we can really have not that high throughput and very fast screening, but we can really screen 2,000 compounds per day and have really single molecule resolution data, which I think is remarkable. Please.
It may be my jet lag, so forgive me if this is an obvious question, but you're talking about picomolar concentrations in a microliter. So that means you've got about 10 to the 5th molecules in your sample. So where does single molecule come in?
Yes. So yeah, that's a very good question. No, it's not. It's a very good question. So with a confocal microscope, we can focus our beam to a very small volume, femtoliter volume, right? So if you have picomolar concentration, and this is also a drawback, I think, of single molecule investigations, but there is also ways to overcome it. That actually we use low concentration and we cannot do it with higher concentration, because with higher concentration a lot of molecules will diffuse through that small volume that is excited by the laser beam. They would diffuse at the same time. So only if we use, let's say, below 200 picomolar, we have the condition that only one molecule is diffusing through that small volume that the beam is focused, and that's how we have our measurements. And in single molecule measurements, you have two kinds of measurements, right? So the data that I've shown you, the second set of data are what we say solution data. So the measurements are really simple. You just would place a drop with 100 picomolar concentration of your sample, and whatever diffuses through your confocal beam, you will measure, right? The other kind of measurements to get dynamics, you would have to mobilize proteins at the surface, and then you would scan the surface, identifying single molecules and measure them. But for our purpose, this is not needed. So solution measurements are good enough, and this can be really made in a very high throughput way by reducing really a lot, the concentrations and the volumes.
So you pointed out in your talk the importance of dynamics, and
Yes.
nevertheless, if you want to look in the classical drug discovery approaches, a static view very often is highly successful.
Yes.
There are many different cases. So can you give some ideas about how many targets will be more druggable by using your technique as opposed to a static approach?
So yes. So if you would see the first part of my talk, I think, of course, usually people see a cleft and a ligand, and then with very powerful computational tools, you can more or less decide which interactions are important, right? But this is actually, it works, but in the case of the first example I've presented, that only one mutation, so only one interaction would impact more than 4 orders of magnitude of the affinity. This you would never find out if you would not discover the binding mechanism of the ligand, of the inhibitor to the protein. So this information you would never be able to see with the classical tools used. And for the second part of the talk, having proteins as dynamic as RAS, I think could help tremendously, at least giving a reasoning to people why successful drugs are missing nowadays. Because if you would have the view of the static cleft on drugs, you see many of these clefts of nice pockets around, and you would think, okay, why people cannot target them precisely and have a very specific inhibitor. But now if you would have the view that this is not a static picture, but the protein moves continuously, and these clefts are reformed, formed and destroyed all the time, this gives a good indication that new tools and technologies are needed to target these dynamic pockets. And I think having a platform like the one proposed on drug discovery at speed of sound can really help really test in a very high throughput way these pockets and see what the outcome is.
We will now have a presentation which is pointing out the possibility of using phenotypic screens as an alternative or as an add-on to biophysical methods. Also a company from Munich, right?
Yes.
Yes.
Thank you very much for the invitation. I'm very happy to be here. I hope I will be able to explain the things we do, since we are mostly biophysicists and biologists. So everything that I will show is actually on cells, almost everything. We are a company that is located in Munich, so another one from south of Germany. We started in 2002, also as a small spin-off company of LMU, so Ludwig Maximilian University in Munich. And as our company grew and got distributed around the world, so did the throughput of our instruments grow. So you can see here from a single cell or single chip system called PortaPatch in 2003. We went to a little bit higher throughputs from 4 to 16 channels in PatchMiner, then switched to SuperPatch 96, which we discontinued lately, as the star of the company is actually the very high throughput system. Well, for us, for cells, very high throughput system, the SuperPatch 384 or 768 patch engine. And what we do is automated patch clamp. So the systems are installed all over the world. Universities, companies, people do different things with them. They either do classical research, either on heterologous systems or on primary cells or iPSC-derived cells, or they use the systems for drug screening or safety applications. So I will focus mostly on this system. So this is the module that you see here on this picture, and I will introduce you into the patch clamp measurements in an automated way of different ion channels in cell lines and iPSC-derived cells, mostly cardiomyocytes, and I will have also a couple of slides with neurons. I will also show you one mid-throughput system, the PatchMiner, but mostly because of this very interesting feature where we combine patch clamp measurement with a real-time simulation, computer simulations. And then at the end, I will touch base with transporters in drug development. So another system that has 96 well throughput and is not requiring cells like the SuperPatch 384 does. So why do we do patch clamps? Why are we interested in ion channels? So ion channels are basically helping our body work. So just the point that I'm speaking now, the way I'm thinking, the way the muscles are moving, the way our heart is beating, it's regulated through different ion channels. And some of them can be nice, so we can taste nice things with them. We can distinguish warm or cold. We can play football with our muscles. But some of them, and actually a lot of them, if they have a mutation or if they are not working properly, either not working enough or working too much, can lead to very serious illnesses, and therefore they are important drug targets. The reason why we actually pushed through the high throughput automated patch clamp systems is because we needed to cover all of these channels in our experiments, or our customers needed to cover these channels in their experiments. system. However, when patch-clamp got invented, discovered, and NEA got Nobel Prize for this technology, it looked like this. So one would sit in a dark chamber in front of a microscope. They would put this glass pipette towards the cell that they would see through the microscope. And then they would navigate this pipette towards the cell and then measure different activities, so different ion currents coming through the cell or the changes in potential inside those cells. And I did that during my PhD, and I was very happy when I had 5 cells a day, and that was my greatest day of the measurement. However, you don't want to do that for all those huge lists of ion channels. And how we started, or how our CEO started in his PhD thesis, he said, I don't want to do this. This is boring. I don't want to sit in. I want to drink beer in Munich. And he made this little small device that has just one channel, but still increases your throughput 50 times. So how this works is, other way around is here. So in this case, you have the glass pipette and you're approaching your cell. Here, you have a hole on a planar chip, so this would be borosilicate glass. It has a little pore here, and the cell is basically coming to you. So we apply small suction, so the cells in suspension are getting to that hole, they're getting attached, and you can perform experiments in different configurations. And this would be the comparable picture. And I also have a little movie here, so I guess now we figured out how it works. Out. So you see here, this is the hole, and you see the cell roaming around, and then at one point it's caught. So this is how that worked for the small machine called a porta-patch. So in this case, you get 50 data points per day. And now, depending on how you are actually organizing your experiment, what is your experimental design, you either look at 2 points, then you would need 2 data points for your compound, or you look 4 repetitions or 8 repetitions. With this small machine, you could do 6 to 20 compounds a day. So that was not enough, so we went further to the patch liner. So this one had 4 to 8 channels at the same time inside the chip. And with that one, you have 600 data points per day, and that would give you 75 to 300 compounds a day. And then, of course, the big companies wanted something that can do much, much more. And this kind of module, and I will show you in the next slide how that is integrated into the liquid handling robot, can perform 200 data points per day if you have 2 modules. So 2 modules can be incorporated in the robot. You can do 40,000 data points per day. That would mean that we work in a plate format. Those are 384 wells per plate, or 768, depending on how many modules are inside the robot. And that would give us between 2,500 to 10,000 per day with one module, or 5,000 to 20,000 compounds per day with 2 modules. And this is how this looks like. So this would be the Beckman robot that we are integrating our technology with. And you see these 2 small little parts. That's basically the entire brain of the machine. It is connected with 384 amplifiers. So for each single cell, you get a unique signal. We perform gigaseal patch clamping, and for those who do not know, that means that the cell is very tightly connected to the glass, and that enables you a very precise and very controlled experiments. As I mentioned, 1 module 384 wells, 2 modules 768 wells, and this system can be left in operation unattended between 4 to 6 hours. I don't comment about the price, but you see very low data point price. What is really important about this system is its flexibility. And I will go through the characteristics and flexibility points that are valuable for the drug discovery in high throughput. So this is how one of our chips looks like, and Of course, you don't have to run the whole chip. I guess all of you want to run the whole chip because that's the point of high throughput. There are 384 wells inside, and they can have different types of hole sizes, different resistances, and this is important because different targets are more or less difficult to patch. So if you would have a cell that has very nice compression of a certain ion channel, and those currents are very strong, then you don't have usually a problem. Then you would use one hole chips, and you have them in different resistances depending on the cell size. But if you have tricky targets, if you have cells that have very low expression, if you have the compounds that are not stimulating the cells strong enough for you to have very high currents or very pronounced changes in action potentials, then you can just switch into another plate type that has more holes, will catch more cells, and in that way amplify your signal. So what you would see when you do an experiment is hopefully always this. So green means good. So all the wells in this case are plated with CHO cells, which were transfected with potassium channel that is important for the heart, it's HERT channel. And if the experiments worked and the cells are open and ready to be measured, the color will be green. Here you see the cutoff that we say, so what would be, per definition, a good measurement. What you see here are just the measurements on different currents, and what I want to emphasize with this slide is that they all look the same, so very highly reproducible, and they are also very stable. So these experiments, and I don't know if you can see the small or very dim blue lines here in the background, so those are the experiments or measurements that have been repeated for 20 minutes. So you have very high stability of your measurements. And this is very important if you want to add different compounds on top of these cells and apply them in high throughput. What also is important, and we have mentioned about the temperature in one of the previous talks, is that not everything works well in room temperature. Well, sometimes it works well, but it's not physiologically relevant. So a lot of compounds have temperature-dependent effects, and the system is completely temperature controlled. And what I want to emphasize with this slide is the change in the current amplitude just by changing the temperature. So if you will look at the same channel that I showed you before, so that one important for the heart, you could see the current that is measured at 21 degrees, so one would say room temperature, and the current that is present at 35, so very close to the body temperature. As a readout, we would have basically the amplitudes or normalized amplitudes of the currents, and that could be very easily plotted inside the data analysis for software, giving you a readout of an IC50 or an EC50. Not only you can measure stably or room temperature or physiological temperatures, one can also apply different protocols. And this is important if you say, let's have you want to have one compound, and then you would like to see how that one compound is having an effect of different types of cells or different types of ion channels. So one of the projects that we have been doing is the project called SIPA, which is important for the cardiac safety. And what we have performed there is we have managed to develop one single protocol that we are applying to our cells, and thereby being able to screen 6 channels at the same time. So this would look like this. You would have 6 different cell lines transfected with 6 different channels, measured in one single plate. Not only you can do that in heterologous systems, as I mentioned before, so those cells are nice and round, they are very easy to get into suspension. Other cell types that are not so easy to do are actually our own cells, so human cells, either cardiomyocytes or neurons, for example. And those are the cells that are very much interesting in biological world these days, as they could replace the animal models. So cells that are represented here are actually human cardiomyocytes. Those are iPSC-derived cardiomyocytes from human patients. And with a little bit lower success rate, so around 70%, we're also able to measure those types of cells inside of this system. So one could basically do a drug screen directly on human cells, not on heterologous cells. Another feature that is usually checked, and it's a new feature that we introduced last year, is actually measurement of a voltage inside this high throughput systems. So that would mean the action potential of your cell. And what you see here are different action potential traces of human cardiomyocytes, so human heart cells. And what you can also do, and what is important for this point, is that you can also add different compounds on top of them and perform high throughput pharmacology. So we can add different compounds, either intracellularly, so we have perfusions that can exchange the intracellular milieu of the cells, or we can apply different compounds on top of the cells depending on where the compound will be predicted to act. So you see here, this would be the control measurement, and this would be the blockage of calcium channels that are performed with amphetamine, and you see the success rate of 100%. This would be your analysis showing one value for the control and then the drop of that value with, of course, different concentrations. I know we talk about sound, but I also wanted to mention light a little bit. So different compounds can be also influenced with light. There are light caged compounds that are photoswitchable compounds that can stimulate or inhibit the cells or ion channels. And what we're working on now is to incorporate the optical stimulation inside this system, so that would be this blue area here. We would stimulate the cells from the bottom, as from the top the robotic hand is adding compounds, so it's impossible. And what one expects from that is basically to modulate the activity of the cells through light. So we could make the cells be more active or less active, which is important for drug discovery and safety as well, as different compounds show activity-dependent effects. So when the channels are open or closed, they would have different affinities to different compounds. What you see here is one cell line, CHO, that was transfected with a sodium channel, NAD1.5. That is expressing channel rhodopsin 2, so that's a protein that will react to light, depolarize the cell, and make it fire, so make it produce an action potential. And you can see that with the pulse, the cells are very nicely following the stimulation. This is highly applicable in preclinical disease mechanism research and drug discovery. One of the publications was from a group in Chicago that looked at different potassium channel variants in autism and epilepsy, as well as the transmembrane conductance proteins, CFTR, so the chloride channels that are involved in cystic fibrosis. So I will very shortly mention our mid-throughput system, the patch liner. And why I want to emphasize this is because I want to also think about different parts of the experiment. So it's not only the consumables or the system or the amount of compounds, it is also the amount of substrate that you're using. And in this case, those are cells. And the cells like heterologous cells, for example, CHO cells or HEX cells, they don't cost much. But the cells that are iPSC derived, so human cells, they do. And in the system, you can see here just the schematics of how the cells are basically introduced and how they are washed out. We can use only 400 cells per well. So compared to 10,000, 400 sounds pretty cost effective. Like that, one could measure human cells, currents, sodium currents here, potassium currents, as well as action potentials, and perform full pharmaca on these. what one can also do is simulate different drug effects. So if one does not have a channel and has a protein that could maybe work with that channel, one can perform the measurements inside the patch liner, and depending on the parameters that are measured, a computer can in real time simulate the effect of different compounds to that cell. And this is something that was, which was published just recently in December. And what we could see is the very nice prediction, which could be also treated in pharmacological ways. So the pharmaca matches the simulation. Another instrument that is semi-high throughput, so for us 96 wells is already relatively high throughput, that does not require cells, is the Surfer. And this is this robot here. It is inside, the module is inside the Felix SciBio robot, so not Beckman in this case. And what this offers is basically the high sample flexibility, as it will not work with cells, but it will work with intra and extracellular, eukaryotic and prokaryotic targets, such as membranes, mitochondria, lysosomes, and so on. And similarly to the previous one, it is also temperature controlled, it is also fully automated and works in 96 well plates. So this would look like this. You have a robot hand, pipetting hand, that is bringing your compounds into the module, which is located here. Your wells are connected to the 96 channel amplifier, so again, pure measurement from each sample. And it follows the automated workflow with a similar software, so there is no, so to say, learning. The learning curve is very fast if one operates both systems. The sensor is here 96 well plate, so it will not have as many data points as the 384 system, but still offers 10,000 data points per day. The system is very stable, so you see again a lot of green, so almost 98% success rates. This would be the current measurements, in this case from a glutamate transporter over time. So this is very initial experiment, and this would be over 12 hours, so not 20 minutes, 12 hours. And it shows you a very nice dose response curve to the application of glutamate. This slide basically explains the way that the experiments are performed. So what one would do is one would load the cells, or in this case membranes, on the chip. And you see here different, I hope you see, the different shades of blue going to the right. And those are basically the times that your solution is exchanged. And in this case, it would be the application of either the same compound in different concentrations or different compounds. So you would do the negative controls, you would do the positive controls, and then you would just apply your compound until you are ready to wash out. After the washout, you can apply the next. These are all the validated targets in this system. So they're mostly eukaryotic, chill membrane associated proteins, as well as, so all of them are symporters, some pumps, and exchangers and enzymes. We have already started here in Groningen yesterday, so I installed a similar system, which is an EFP measurement system, so extracellular potential measurement system, with a 96 in 96 format. It is used in many different ways, so from disease to the pain assays, and for us here relevant the drug screening. So this is already in-house and can be used. And with this, I will summarize the points that are relevant for this group here when one thinks about the automated patch lab. What we were able to do at Nanion was to successfully establish the assays for the automated patch plant targets, ion channels, transporters, exchangers. We are able to perform the phenotypic high throughput screening, as I mentioned, to the levels of 40,000 data points per day, or 20,000 compounds. The assays are plate-based. They use low liquid volumes, which would enable the test of low amounts of compounds. They are already running on established protocols, not only on heterologous systems, but also human cells. Last but not least, I think one of the previous speakers also mentioned the analysis. So when one produces that much amount of data, it actually means nothing if you cannot really read it. So we integrated the software packages to the systems that we are generating in Munich that enable very fast data analysis, and what you get at the end is an IC or AC50 curve for your compound. And I'd like to thank you for your attention, and I hope you could grasp the biological side of this. I know it was cells all the time, no protein, no crystals. And if you have any questions, I'm here, and I'm also here tonight, so we can also discuss that. Thank you.
Some questions from the audience to the introduction of phenotypic screens, optimization screening.
Yes.
So can you apply this to beer? Can you have a beer come to the company so your founder doesn't have to use
No, but what you can do is you can drink beer and then give a little bit of blood and then measure red blood cells, which we actually did, and look at the currents before and after beer. Would that work?
phenotypic screens of alcohol?
Yeah. Yeah, we actually did that to test some other features.
What was the result?
Well, it was random, but I'm actually pretty sure that some people lied that they had just one beer.
So you cannot use it for quantification of alcohol. It is a very expensive method.
No.
Instead of blowing in a tube.
No, I would not. It's also
recommended.
not portable, so.
It was a psychology experiment.
Yeah.
Thank you very much.
You're welcome.
And the last speaker of the day is again from a company which is doing biophysical screens, which in our opinion is also very suitable for these fields of technology.
Okay. Welcome everybody from my side as well. I want to tell you a bit more about high throughput SPR today, coming from a company called Forte Bio. So Forte Bio actually is a typical Silicon Valley company as well, starting in a garage. And what they did nearly 20 years ago is they turned the world around by using biosensors for biophysical characterization. Everyone at this time brought the sample to the sensor surface, and the BLI technology of Forte Bio actually brought the biosensor to the sample by dipping a glass capillary into a microtiter plate. But this is not what I'm here for today, because as we are now part of Danner, so we belong to a big family of very well-known companies, and Forte Bio is a division of PAL Corporation, which is more or less well-known for filtration technology, but nowadays we are trying as well to cover the whole field of biopharmaceutical manufacturing, as well as various areas of filter technology, including medical applications, water, and so on. And the biophysical characterization comes here on the point where you want to check if your protein is fermented, if it's pure enough, and so on. So what we have acquired last year is the company Session3, and this is actually, and this quote is from Tony Gianetti from Genentech, the first innovation in SPR for more than 20 years. So what Session3 engineers actually developed is a new kind of injection. And this is what I want to show you today, because this type of dynamic injection allows you actually to measure a lot more samples as you could on a conventional SPR system. So inside the system you have 3 channels, and the Pioneer FE system is optimized to do fragment screening or small molecule screening, as we would say. So the reason behind this is you need a very high sensitivity of your instrumentation so that you can actually cope with the concentrations which will be available on site to measure such compounds in molecular interaction with your target you want to study. And it needs some things to take care of, like control channels, negative controls, and so on. So the system itself is optimized to do this kind of work. And the novelty, which is now inside the instrument, is actually what we call one step, because rather than in the conventional way, where you would inject one concentration after another from a dilution series to gather a kinetic characterization of your association, dissociation, and out of this KD of affinity, you would just use one concentration, and this concentration actually is diluted down, passing through capillary, building you a gradient of your compound before it hits the biosensor. And by doing so, you will get this typical curves, binding curves, which can then be modeled as in the same way as you would do with the conventional SPR. And the next slides will actually show you that this is more or less very much comparable. So here in the upper one, it's what I described. So you have a couple of concentrations which you would inject one after another. So you have a series of several injections which take you a certain time amount of X, and with one step gradient injection you have only this at one time. And the information you can extract are comparable to the small molecule kinetics in the conventional SPR. This results were collected on a Biocore T100. Speaking of that, you can speed up your analysis by using just one injection in comparison to this more than one injection. Means as well that you are saving a lot of time, because all the preparation up front, doesn't matter if you can automate this, has to be done. In our case, you can actually use your compound out of the library and can inject it directly, and you don't have any workbench work to do in preparing your sample for the analytics. And you will as well reduce the sample requirement, because what you get here in a classical way is usually you do a primary screen in drug discovery, where you just look which of your compounds would interact with your protein or receptor of interest. And then in a secondary screen you would do the more sophisticated kinetic characterization. But with one step you bring this already into what we call the primary screen. So you will save as well a lot of compound because you are doing this just once. And the assays are of course simpler, faster, so this means there is less possibility to make any errors. And as I said, the instrument itself is optimized in a way that you really gain the high sensitivity. And just to underline this on the next slide, you see as well a couple of examples where you have the direct measurement of the single injections, and you see that the KDs of the traditional SPR and the one-step injections are again in the same ballpark. As with other, or each technology where you can produce a high amount of results, it's here as well very necessary to have, of course, the software behind. So the software comes as an integrated package of this instrumentation as well. So what it allows the user actually is as well to predefine certain thresholds. What's a good compound, what's a good binder or not so good binder, and this actually is fed already into the software, and the software will then more or less on a one-click base lead you through the analysis from your raw data through the reduction of your controls into the clean results, and these results will be very quickly ranked. So this is not very well seen with this beamer, but this is actually data from the MyBridge library, and you can see actually how the positive control looks here. So this is negative control. It's not seen because it's in the line, and you see then the hits you have. And these hits are actually as well ranked in a way that you can find them in a graphical order, whatever you prefer. You can as well get this as an output in form of a table. So this is what I said earlier on. You can predefine what is a good binder, and the software will actually on ligand efficiency list the compounds you have actually measured in your experiments and rank them to your predefined thresholds. So in terms of how would be the assay design look like, so as we are working in an SPR platform, it's similar to the conventional technology. So one of your binding partners is immobilized to the sensor surface, and your analyte of interest is brought to the biosensor surface in a liquid system. And this means, of course, you have to do some pre-work by bringing down the target molecule of interest to the sensor surface. And you would as well run a positive control to make sure you see real binding. Negative control, of course, as well important to detect any non-specific interactions as well. And then you would prepare your fragment library buffer to measure it via the biosensor, and if necessary you can do a couple of blanks or whatever you want, just to have some data sets to correct your data as well and clean them up. As said, primary screen, secondary screen, competition assay, something I will leave out today, but the competition assay very quickly just is something people do in drug discovery as well to make sure they don't have false positives. So what they do is actually they use their target of interest. It will be inhibited with a molecule they know already and have well characterized, and then they measure against this inhibition, the binding So this means, can my new candidate actually replace this already well-binding molecule? And this is what the instrument can as well help you with, because it's something we call next step, but this would be a topic for another workshop, where you actually measure in this dynamic injection the replacement of an inhibitor. And then, of course, when you have prioritized this, you will do the crystallography as we saw earlier today. And here it's just again shown where you measure actually your data, you select your hits, and you determine your affinity. But in terms of affinity, it's the whole kinetic profile, so it's the on rate as well as the off rate to determine your affinity. And what's important as well here for this workshop, with this one-step approach, you can actually run 768 samples in 24 hours. So this is something the instrument would handle as well, fully automated, as you have two plate positions on the sample deck holding both 2, 3, 4, 8 plates, which are measured one after another in 24 hours window. So this is just to summarize now. In usually the primary screen and the secondary screen, you get your characterization, but with one-step approach, you do this already in one screen. And the competition assay would be what I just briefly mentioned, the next step, which can be done on the same platform. So the conclusions, make decisions faster, collect more data, and push the ones you think are the best in class, rather than just sitting there for more than 2 weeks by doing a primary screen and a secondary screen until you can wait. And this is animated now to make a decision and bring the drug faster to the market. And beside this, you have time and cost savings, because you don't need any workbench preparation beforehand, and you get more measurements in the same time. So it's unfortunately animated in some sort, so it's jumping all the time. So 768 fragments in 24 hours. You can perform more than one assay type on the platform, and the data analysis comes straight forward as this QDAT software is integrated, and you have a couple of more advantages by using the system. So if you want to find more, you have a particular question now, please feel free to ask, otherwise you can find this as well. Thank you.
Questions, please?
I'm sorry, I think you mentioned it, but I just missed it. What was the actual volume in each well there that you were using?
No, I haven't mentioned that. So usually for the time window you would use for an interaction analysis, which is about a 1 to 2 minute injection, you would calculate approximately 15 microliter of sample. And it should be in a certain concentration range, so that you will have a good concentration range, because the gradient we produce is something which will comparable to a 3 to 4 log dilution series. So you have, if you have a 1 micromolar approach of molecular interaction, you should somewhere start as well in the concentration range on micromolar, otherwise your
how difficult is it to put your protein of interest down to the area where you're actually doing the SPR so that you can monitor the change? I mean, do you do that just at random? Is that just a random chemical?
No,
scan?
no. We actually offer several sensor surfaces which are prepared, so that you can actually very easily immobilize your target of interest. So covalent would be the easiest one, but it's the one which is less preferred because you don't have any control over the orientation on the sensor surface. But we are offering as well several tags which then capture your molecule of interest on a certain position, so that probably the target pocket, whatever you want to measure your compound against, is always in the right position from the sensor surface.
How does SPR roughly compare to some of these other surface interaction technologies? So you have this biolayer interferometry, right, which I think is a bit less sensitive. And there's this other thing that I forgot the name of that allows you to measure interactions in multi-well plates.
So yeah, this is probably something you can discuss very much in detail. So I would say the community would agree that the SPR is the golden standard. So the reason for that is that it's the technology which is longest time around, and the market leader is SPR, and everyone has actually to measure against this market leader. And as I said initially, then the BLI technology of ForteBio came into place. So they turned the world around with something very intuitive and new by bringing the biosensor to the sample. So it's non-destructive in the microtype plate, but we already named it. It's not as sensitive as SPR, and particularly if you're looking into fragment screening or very small molecules, we need this type of sensitivity to cope with the variation of concentration as well as we've seen this morning. So you want to work in amounts, which means you are very limited in concentration, so you need a very sensitive system, and this is something I will not cope with. So this was the reason actually why we acquired this company, because we felt we have to close this gap down to 70 Dalton. In one way, either you have the sensitivity that you analyze can be smaller, like 70 Daltons, or the concentration can be increased, and you see the signal is still lost. Anything else? No? And thank you very much again.
So before closing the workshop, I would like to remind you what this workshop was about and what our goal is. Our goal is to win this this grant, which should amount for several millions and which should pay for build of a prototype and validation of the platform. And we have done a lot of pre-work in order to assemble the right companies, the right groups, the right instrumentation companies. We already talked to a lot of different pharma companies where we could get more or less ideas to which degree they are willing to contribute, and we have invited many of these representatives from the different groups, and now we would like to get your input, how you see that we can continue, and just to remind you, for this Perspective grant, which is a public-private partnership of the Dutch government, it needs 15% co-payment. We want to go for the max, which is 4 million, and that means we have to get 600,000 co-payment from the contributing, participating companies. And there are also timelines, so we are now in phase 2 of this grant application. Middle of February of next month, we will get the information if we are in the final round. In the final round, there is only a handful or 2 handful of competitors, and I already pointed out that I believe that we have really good chances because we are the only application. The applications are public viewable, so you can go to the web page, and we are the only ones who are dealing with chemistry and drug discovery and health. And these are 2 of the top sectors of Netherlands. So already 2 are represented only by our grant proposal. So therefore, and we have a high caliber group of potential collaborators and partners, and therefore I'm very confident. Nevertheless, the time is running. If we are amongst the selected 2 handful of proposals, then we have to come up with the consortium, including all the work which has to be done in order to make sure that the money from the contributors is also coming by middle of May. So there is then only 2 months, a little bit more than 2 months left to the final work. And so this is a little bit the background, and of course I know that we cannot do any decision right now, but I would like to ask the representatives of the different groups what their opinion is about the day and what their ideas is how to continue. And we have 3 different parties or 4 different parties. So we have the public parties, which is us, the universities, and we have the big pharma partners, the potential big pharma partners. We have the instrumentation companies, and for the high throughput crystallography part, we have the 2 beam names, Daisy and Diamond in Oxford. So I already talked a little bit to some of you guys. So Michael from AstraZeneca, maybe you can start and give us some impression of the day and what you think. Exactly, and that's what I'm looking for. The first one is...
the account is empty.
It stops dropping.
No, it has been really interesting, and I really enjoyed it. And also, I think this is a very nice one of many approaches into the future to do it. I mean, definitely not the only one. So there are other technologies in everyone's screens and has good ideas. But for making really high throughput on a high speed fashion, is really going, I think, into the right direction. If we don't make the same mistakes as 15 or 20 years ago. And we had recently internally a long discussion, and our idea is to have fewer cycles but more data. So to generate as many data as possible, leading to fewer cycles to come quicker to the answer or to deliver the drug. And everything around high throughput screening, around acoustic dispensing, all the technologies we saw, I think it would be really cool to see this driven through such a consortium, because from my point of view also this is all pre-competitive. Not even if someone goes and does this alone, this will not necessarily be a competitive situation. It's like all screening technologies, and so that's pre-competitive. And if we do this together, we can learn from each other and drive this much faster to the benefit of our individual companies and institutes. It's with everything I show, for example, I have at least 3 times more questions and unknowns how to progress things, and I would be happy to discuss this in a consortia and really see what other things other people think and how could we solve problems that.
Thank you very much. I also would like to mention that several parties here in this room are part of the European Lead Factory, and the European Lead Factory is also supposed to be a pre-competitive grant, and that it basically is a grant where more than 70 different parties were involved, not only the big pharma companies and the universities and the CROs, but many more, and that was a grant which amounted to almost 200 million, so one of the largest European grants ever, and it was doable. So we are talking here about a very small grant. Nevertheless, these 4.6 million are important to build prototypes and to show that this system is working. So I have to say I'm positive from my previous experience with the European Lead Factory, where I thought in the beginning, oh God, this will never work, because there were 10 times more lawyers in the room than scientists, okay? So, of course, this can happen here as well, so there is currently no lawyer, but at some point lawyers will be involved.
I was pleasantly surprised that in the end we synthesized 200,000 compounds, and when we started we were like, how are we going to do that? But you know, you learn along the way and it worked, so it was not over-ambitious. I think also the current proposal is quite down to earth. I don't think it's over-ambitious. I think it can be done. I see this as a big step in screening. I think the synthesis part will become more important. At least that's what I see myself in the lab.
If I can throw a question out there, and particularly to our target audience, which is you guys from the big pharma, where do you see the bottlenecks in what we're producing here? Where do you see the problems? If there are none, that's awesome. So we'll accept the money.
I think the biggest obstacle is usually to get senior management convinced that this is flying. And that's why it's always nice to have like proof of concept, which has been shown by Michael actually. So, I mean, if that would be part of the pre-competitive space, I would be more optimistic that this is flying. Because you have shown already that it's an integrated approach and that this kind of works. So, I mean, knowing from working in consortia, it can be quite time consuming, and sometimes you really have to wonder what you get out actually. It all depends on how it's being organized, so that's a critical question for me. And also like really having a business plan which I can take actually to my senior management. That's something where it's clear what's the goal. So I mean you outlined it, but I think it would be good for me to have something also on the slide or a short presentation, elevator speech type, key points on the slide deck or in a small document. Because to me it's not like quite clear actually, what do we want to achieve actually?
In timely, because I think the timelines are kind of tight, right?
Yeah, no, that's why I'm asking a very honest question is, what would you need to bring to senior management for them to say, yes, let's do this? I mean, we're talking about 600,000, which is real money, but we are going to divide it, that number has to be divided by the number of partners, so it can get quite low, but it still is a real investment. So what would you need, assuming you're convinced by this approach, what would you need, in your opinion, to take to your senior management to say, let's do this mid-May? Proof of concepts, we can generate more data on showing that the reaction mixtures do provide molecules you can detect in situ.
I need a bit more clarification about exactly where you want to position it in the drug discovery process. For me, it seems like you were covering the screening part at the beginning, but also that you talked about hit to lead. But I mean, that's a broad span, and I'm not sure that what you described as really hit to lead. It's the beginnings of, but it's not quite the
I mentioned that these are certainly not clinical candidates which you get out of the genetic algorithm, but you get optimized compounds, at least for the parameters that you're looking into, which you put in the selection process via genetic algorithms. But from these different highly potent compounds, you get there is still a route to do tiny nitty-gritty atom exchange here and there, and
do you plan to incorporate that as well? I mean,
well,
sort of optimizing a particular structure, not expanding into chemicals.
I think as long as it can be performed with this kind of chemistry, which still allows you to produce numbers of compounds. If you are in single compounds where you have to put a lot of effort into getting specific starting materials which you do not have access to, then this is out of the scope of a miniaturization system. There is no point in miniaturizing this because then you are left with the classical problems of medicine and chemistry. So this is not what the platform can deliver. So we can bring you very fast against different types of parameters, from millimolar inhibitors to nanomolar inhibitors. They can be optimized against several parameters. We can provide you several starting points at the same time. But then, of course, there is still a way which you have to go through clearly, in order to do all the initial PK, PD, and whatever is needed to come to a clinical candidate. I mean, this is not everything is automatable, but at least a considerable part of these 4 to 5 years, which I showed in the beginning, can be shortened, and this is what we want to accomplish.
I think into these programs in their own right, that's not the goal. The goal is proof of concept and connecting the different efforts and delivering protocols that are easy to follow. Take the chemistry without descriptions on how to do this. It's very difficult to set things up for a percentage cleansing. So I think that's one of the things that this will deliver descriptions on how to translate things to other places.
So for us, the timelines are also very challenging, I would say. Mid-May, seeing what has to be done until then, and bringing in the lawyers probably is really a challenge. The more so as the current proposal is phrased out in a way that it goes really for the full thing. So it's very, very ambitious. And I think it would probably be better, and it would make our lives easier if we could say, see, this is probably the picture in the future, but there are small fragment parts of this which also would be a big gain for us if we could implement these kind of things, and that would make it probably more easy to sell to our management. The full picture also, after what I've seen today, is that, I mean, some of these areas are really well advanced. The other parts need to be very much worked on to be fit into this picture. So I think to convince somebody that this can fly indeed within the next 4 or 5 years is a bit challenging. If we isolate some of the parts of it, could be easier.
I mean, that can be done, but your senior management has to realise that when you write a grant proposal, you of course promise to get.
Sure. I mean, this is very clear.
What you actually deliver is.
No, I think you want it to be a bit more down to earth, right?
Yes.
I think that can be done.
Yeah.
We can certainly re-see that proposal and put it into a more concrete deliverable term. And hopefully something that then with your support you'd see as, yeah, that's achievable within a 6 month, 24-month time frame.
Maybe I can add one sentence or a couple of sentences to this. For me, there's clearly 2 phases, and I think even in the proposal there are 2 phases, right? One is plugging this stuff together, which is challenging already. And the second part is really proving that it works on real examples. And what would be extremely helpful would be, I think, also to sell it to senior management, would be an example that is foreshaded in the proposal. That we really can say, okay, we're having the synthesis, which is kind of sure to work. I would say. I mean, there are problems, but probably they're solvable. Then putting it together with the analysis, QC, and screening, where I do have question marks actually. Especially since you would have to decide relatively early on what type of assay or what type of physical chemical measurement you would use and make to eventually get to a point that you can use it for a project of interest for the pharma partners. Right? And that is already playing into the second phase, really proving that it works in a kind of real life scenario. And I think the proposal should probably fall into these 2 parts, because I think it's challenging to finish the second part within the 4 years. And that's probably similar to what Martin was saying.
So I've got a question for both you and for you, that you said that there were parts that what gauging parts of the car. What parts specifically are the ones that would be difficult to convince senior management on?
The machine learning part, that's
Pardon?
always, any machine learning component, that's always the one I get the questions about. So, I mean, you talk about these genetic algorithms, but I don't know. I'm also not an expert, I can't judge it, but that's always the questions that come. Machine learning. Designing the next step.
So I totally agree to all the argumentations, but on the other hand, I also would like to remind you that all of the components already are around, and that there was a company 20 years ago which was called Morphkin, my first startup, where we were running exactly this as a business idea, and we were collaborating with some of the companies here in the room, and we were taking their target and starting with nanomolar inhibitors and using genetic algorithms that time to bring them down to nanomolar inhibitors, and this was done over and over and over again. So the difference between the 20 years ago and now is that we have much more suitable technologies like acoustic dispensing, which really allows us to to shorten the cycling times, which is extremely important because we are talking about bringing the cycles down, and we have much more advanced screening technologies. So I think if we are able to combine these novel tools which are around now and having in mind that in principle the system has been shown already in the past to work, in the incorporation of artificial intelligence genetic algorithm, then and this is published, and so it should be maybe could be helpful for your management. Of course, this has to be presented in a proper way.
But you can also argue that the genetic approach is one way to analyse the data that comes out. Of course, you can still take a standard ranking, cherry-picking human approach and say each cycle this is better. It may be slower, that will be the hypothesis about it, or the thesis about it, and it wants to be true, but still just by cherry-picking along it, you're still going to see improvement per cycle. So I don't see the genetic element as a point of failure within the protocol. I think it adds a lot of value to the approach, but it's not something where if that doesn't work, the entire thing fails.
So I think there are, of course, a lot of challenges in this whole area along all the topics we mentioned here. But that's why there is this, or why there's the ambition for building a consortium. We can raise challenges, but if I never address them, I will never solve them. So, and I think also, what was it, 150,000 or 200,000 euros per party, something?
Well, we are talking about the total co-payment of 600,000 euros divided by, let's say, 4 or 5 paying companies, and this is a 4 years project, so you do not have to put the money up front, so we are talking about a ridiculous amount of money, at least when I'm thinking back about the pharma times of less than 50,000 per year. I mean,
that's for big pharma. This is a peanut, but this is really not much money. But again, I need to ask senior management, and the only question they will ask me is, what do we get for the money? I can convince them with the whole area, and they understand that there are challenges with machine learning and everything, and we will work on that. But what do we get out of this? That's what I would need for you. They will clearly ask me, because everyone asks the senior management for some money. I ask them every year for a pay rise.
Maybe I can add to Michael. I think it's a very, very valid point. And when I go back and present this, I will also be asked how many closings or targets can we actually address in this collaboration? What level of hits or leads or whatever you wish to call it will we get out of it? So what kind of very down-to-earth outcome can they expect from this low investment, which still is an investment? We could also do other collaborations and then use the money otherwise. So I think it would be very good to have some kind of what's the realistic outcome, what kind of risk are associated with this investment, what kind of basic outcome can they expect to be presented within 4 years' time?
My response to that would be, in the event that it works, which is of course the caveat to everything scientific that's new, essentially what you'll have is access to a screening platform that costs you whatever your contribution is over 4 years. And then that's a question for your accountants to say, what does a standard screening campaign cost us compared to what they're asking? Yeah? And then you need to factor in the risk of success. Yeah? But if that comes out as a yes, and my proposal would be, but I don't have these numbers to my hand, you do. But a high throughput campaign and development, presumably this is significantly more than the money we're asking for by orders of magnitude.
And I think that's the same problem that we face with every consortia, because every consortia has great ideas. The question is really how we've been in many consortia, and a lot of them have not been very successful for various reasons. One being that there is no clear management, project management of, and then communicating the results back to the leaders actually who pay them.
But then installing some kind of pharmaceutical industry management board to help streamline this would potentially be a way to mitigate the risk?
Yeah, I mean, I'm part of the ACS Green Chemistry Consortia, where all top 15 pharma companies are actually in that consortia. They have specific project managers who run their meetings very, very efficiently. It's very professional. And they actually, because everybody is from the pharma, I mean, like everybody has to put in, usually it's extra work that you put in the consortia.
Of course.
And then you have to get the people really to work on certain tasks, and that can be quite a challenge to really get the pharma, especially the pharma people, because we have other responsibilities, like everybody does actually. but you have to, yeah, really managing how the consortia works is really critical to me. And to outline that to senior management, because otherwise it would say, oh, it's another consortia, so we'll.
So that they want to, if you
that's
put
why I
your
thought
euro
in
in,
the business plan, I mean, really to outline what are the key goals that we want to achieve realistically. Benchmarking, I think, is important, as was mentioned.
but in principle, if you put a euro in, you want to be able to control in what direction it goes. To an extent.
Let's say you want to make sure that it's professionally handled, the money that you put in. That's
Okay,
that's what I get from my
that's
students.
different than making sure you know where it goes. It's
Exactly.
ensuring responsibility of use of resources.
Right.
Can I ask a question? Thanks. So what happens after 4 years? We've been talking about return of investment and so on, and what really are the end goals? I've heard how many projects can we run. So probably we will not be able to run a lot of projects in the first 4 years, right? But then the thing is set up. So what happens?
Okay, several scenarios. One, nothing didn't.
That's easy.
Yeah, that's easy. Best case scenario, nothing, because we've already solved all the problems. Yeah? Somewhere in the middle of those two, you're hopefully going to have a validated system that you can choose to then ideally implement in your own companies as standalone, or potentially take forward some kind of consortium. But this is, I think, best answered once you know how successful the approach is, as to whether or not this is something that your company would say, right, we're going to invest 120 million in doing this in our own doors, or we'd rather do this as some kind of collaborative venture with academia.
I mean, I also would like to remind you that since several parties here are part of the European Lead Factory, we are facing exactly the same problem. So we were investing 5 years, almost 200 million in kind, in the cash in this project, and now it's not clear at all how it continues and if it continues. So, I mean, this is a valid question, but this is of course something which is very difficult to see in the future. And I mean, you can have plans, and we can outline plans, and we will certainly have plans, but what exactly is happening?
I think after 4 years it will just deliver proven working protocols that you can simply copy to run it independently, for example.
You'll know which screening platforms to invest in, ideally, those which not to invest in this context. You'll have a list of targets that have already gone through and shown to be problematic, hopefully, and you'll have a list of targets that have gone through and shown to be amenable, hopefully. What you do with that is, of course, your own business at that point.
You will get the answer where we were promising too much and where things are really working. I mean, 4 years' time is a lot of time where you can show which type of this bombastic chemistry space is really working. If you bring it to acoustic dispensing, there will be a lot of quality control. Then you can see how does biology deal with these impure mixtures of compounds, which certainly are on the table. How the genetic algorithm can deal with these kind of vague type of information which is there, which of course is depending on. So I think this is very valuable information which you get at the end of this project.
You're not going to get a plug-and-play system you can just buy off the shelf. No. But you'll get something that you could potentially more rapidly streamline build yourselves. And as a left-wing scientist, my dream would be that you guys all come together and we just do this on a huge scale. Everyone all joins in together and we hold hands and sing on my eyes. But then again, I am very left-wing. I studied with Tom, so please.
I tried to read a bit about this grants on the Dutch page and I couldn't understand it. But so what are the constraints from the funding body in the Netherlands? Who owns the IP? What can you do with Big Pharma? Can you share things with us? These are certainly questions I will get and our legal people will chase you with right away.
I think these things need to be agreed upon in a consortium agreement with all the contributing partners, probably as a co-owner somehow.
They don't have clear rules, so you will not find on the NWO side anything about 50-50 sharing or something like this. So this is up to discussion. So this is where lawyers from NWO will be involved with your lawyers, and we come to an agreement what exactly can be done in this grant. And so this is something we have to sit together as soon as possible if you are interested in.
But I think the timelines that were raised before are even more crucial, because that can take a year or 2 years just to agree on that, as I use my experience. So I think that's really important to get started.
Hopefully this does not take 2 years or something like this. Again, European lead factory was done in less than a year, and it comprised 70 partners and 8 of the biggest pharma companies in the world. So and there were also tons of lawyers around. I think it can be done because this is a very small consortium, but if there is a will.
And then for the investment we're talking about, my strong suggestion to you guys would be don't put in your real IP hot products, because that's not going to be a good profit to loss ratio. Put in something that you're vaguely interested in, where the IP becomes less of a problem, and then should it prove to be successful, then you can start to invest in your hottest targets. But then that discussion about where the ownership of your IP can come in at that point. Because then you're not helping to build the system, you're using it.
I think no company will put in proprietary targets or anything where we believe that there is a strong financial interest for the company. So I think, to me, we can only work together in a pre-competitive space, because that makes it easier, the rules are clear.
But isn't this all about technology and capability development?
Yes, exactly. Yeah, that's where I think where I see the value actually.
Yeah, exactly. And that's how I
it's about technology, of course, but to run the technology, you have to include targets. But these can be standard targets which are known since many years, and
that's why I like the idea to build a benchmark. Here we had a target, we work X amount of time on Italy, blah blah blah, and then try the same with the new approach.
But then your concerns about IP are associated with the target you decide to put into it.
I would take a dummy just to show proof of concept that the whole methodology works.
And then to an extent, I hope your question will be answered. The IP is not that valuable. No? The process is valuable.
Process insight into how things are fitting together. I think really a major challenge is to bring really the chemistry on speed, that it really works more or less predictably, and with the suitable quality control. I mean, we have seen these couple of examples today, which is just nothing. I mean, it really would, in my opinion, need hundreds and hundreds of different reactions which we have to test and bring on. And this is, as Luke was already mentioning, I mean, this is extremely high value in my opinion, because these protocols are available and everyone can repeat them for their own systems, where you are behind your screen and no one can see what you are screening for. and also what kind of building blocks you have that you come to know the IP and so on.
So if I can comment too, I mean, as an instrument maker, whether it's the hottest project you have or whether it's something in the public domain, we actually learn the same. So on the other side of it, we'll be just as able to make use systems with a lot of proprietary work, whether we start out with proprietary work or with the model system. And it's a lot easier to share. So I think actually having some kind of joint steering committee that can select a good public domain model system that allows us to learn is a really critical element to success. And as we built multi-party consortiums with pharma, that's generally where we start with some kind of joint steering committee to pick a good representative model system. No one has proprietary concerns about it. And that's sort of what we recommend doing in this case. And sort of getting representatives from the companies to figure out what that is and just work at that. I think the other thing that's hard to see at this point is if you actually have systems that work really, really quickly, that makes you develop things even faster. You heard an example today. We're having like kinetics, from the mass spec system, allow people to do assay development of new things. So I'd say maybe this seems like it's going to be slow, but you're applying the metrics of the tools that you have today. The whole goal of the consortium is to make everything go fast. So imagine how fast you'll go when you actually have that tool that's much faster. So I wouldn't underestimate our ability to accelerate our own development as we develop our own tools, because it will be very powerful, especially when you get into the back end of the program. Lots of people having systems and having tools that go quickly will actually be able to go a lot faster through your system. So I guess maybe I'm more optimistic because I've seen this cycle work a couple of times as a tool maker. The science is still hard, but we'll give you platforms to really investigate the science quickly. And again, I think we shouldn't underestimate that ability to self-accelerate as we go forward. The hard part that I've always had is not been the technical part. It's always been the lawyers. So quite honestly, I would want to figure out how we could accelerate the legal process to get to agreement fast, because then the science can take care of itself once the lawyers legally get rid of the proprietary activities, get rid of the lawyers. I think we'll be fine.
And also there need to be an incentive for the people who are in the consortium, like in the ACS actually, the incentive is that we make publications for each of the subgroups. That's the incentive for the individual, from everybody, from academia, from industry actually, to publish something. That's why I think it's only really making sense if it's not competitive.
Yeah, absolutely.
These are all super valid points, and we have learned that management for such kind of big consortia like the European Leaf Factory is key. I mean, otherwise it would never ever work. And we have learned this. We know that we have to produce a business plan, and on the other hand, we also know, because there are timelines, and we cannot move the timelines that we have to deliver. So we hope that you will be part of it. That's what I can say, and we really depend on you. And I think there is a very, very nice group of interested people, interesting companies providing interesting tools which we need to work on this idea. Okay, so yes, please.
So just a proposal regarding the next steps. It seems that the pharma people all have the same concerns, basically. Would it make sense to have sort of a pharma roundtable where we try to do a collection of all the questions that need to be addressed, and then hand over this list to you so that we can really concretely work on the next steps? I mean, time is running, and I don't see a lot of alternatives to that, I'm afraid. So what is your opinion on that?
Yeah, makes a lot of sense actually.
I think this is a very good idea, because you also have to understand that many of the things which are concerning IP and what exactly we can, what is going to whom, is something we cannot even decide. So we have to go back to the NWO, and they have their own lawyers. So we have to have this list of questions from your side as soon as possible, that we can go to Utrecht and discuss with the people, and then we even can go together to Frankfurt, to Sweden, and to the different companies and discuss it face to face. That's the only way, in my opinion, how it could work.
And also, if such a roundtable existed and you could produce some kind of collaborative document, that would be gold dust to take to the NWO in the event we can go forward with the funding. Because we would show immediately that we have not just a single industrial interest, we have a family of industrial interests that are coming together at this point, and they all see this as valuable. And this would help the ultimate chances, if you convince the senior management, the ultimate chances immeasurable. Yeah? Because it then just wouldn't be one partner representative, it would be a community.
And I think the way it normally works, and correct me if I'm wrong, but even if the grant is awarded, ultimately the money will only be wired if the IP is fully agreed upon. Right?
I need a lawyer.
Will be one of the questions for me.
I have one NWO project where there is co-financing from a pharma company, and they have to commit for the full duration of the. I mean, it cannot be that after 2 years someone's jumping out, especially here since we are talking about a relatively low amount of money of contributions. I don't think this is. I think it must be as clear as possible from the beginning, and I think there are certainly areas where things can move a little bit back and forth, but the general agreement between the lawyers of the grant funding organization, which is public money from NWO, and the pharma partners and instrumentation partners must be crystal clear from the beginning. So I think basically we have this time till middle of March, May, sorry, to handle this and come to a final event. So I think what you propose that a list of questions, this will be extremely helpful for us. We will immediately go to Utrecht, discuss it with the people in Utrecht, the funding organization, and then we can talk one-to-one or in groups together with you guys and see how we continue.
Maybe we can sit together at dinner actually.
Yes, yes.
Okay. First of all, a little bit of thanks to the organizers of the workshop. Especially, I would like to mention Yolanda, my secretary, which was doing the bulk work, all the correspondence with the different groups in the room, and all the different people in the lab which were presenting their material today. Dino Centralfonas, Craig was very helpful to bring the right people in the room in the beginning. And at the end, tonight the mayor of the city or the vice mayor will come and give a speech. We have the glasses to drink some wine. And of course the NH crew of the hotel as well.